In the emptiness between stars, in the shadows behind light, the universe grows cold. Not just cold as we know it, but cold beyond imagining, where time slows, where motion stops. Tonight, we drift through these frozen places. Welcome to the coldest corners of the cosmos. The concept of cold has fascinated humanity since we first gazed at the winter stars. We built shelters against it, created fire to push it back, and wrapped ourselves in layers to survive its touch. But the cold we experience on Earth is merely a whisper of what exists in the vast reaches of space. Imagine a cold so profound that molecules cease their dance, a cold where atoms barely quiver, a cold that stretches toward the very limit of what is physically possible. These places exist, scattered throughout our universe, waiting in patient silence. Our journey tonight takes us from the gentle chill of Earth's poles to the near absolute stillness of laboratory quantum states, from the frigid voids between galaxy clusters to the peculiar coldness of a dying star. Along the way, we will discover that cold is not merely the absence of heat, but a presence with its own character, its own story. The universe began in fire. For the briefest moment after the Big Bang, temperatures soared beyond comprehension. Yet for most of cosmic history, the trend has moved inexorably toward cooling. The universe expands, energy disperses, heat dissipates. This is the arrow of time, pointing toward an ever colder future. As you listen, perhaps wrapped in the comfort of your bed, consider that the warmth around you is precious and rare. It defies the natural tendency of all things to cool, to settle, to grow still. Life itself is a temporary rebellion against the cold that waits beyond our atmosphere. The cold of space is patient. It has existed for billions of years and will continue long after the last star has dimmed. It shapes galaxies, preserves ancient molecules, and creates conditions where the strangest physics emerges. In these temperatures, reality behaves differently than we're accustomed to experiencing. Tonight, we speak in hushed tones about these silent places. We travel to regions where human bodies could never survive unprotected, where even light seems to slow its pace. The coldest places in the universe reveal secrets about the nature of matter, energy, and time itself. So close your eyes, breathe slowly, feel the warmth of your own body, this island of heat in a cosmic ocean of cold. As we begin our journey through the most frigid corners of existence, remember that even in the coldest darkness, there is beauty, wonder, and profound peace. Let the gentle cold of distant space wash over your imagination as we explore the ultimate winter of the cosmos, one frozen realm at a time. The cold we will encounter defies human experience. On Earth, our coldest winter night might reach -40 degrees Celsius in the harshest regions. But in space, temperatures regularly plunge hundreds of degrees lower. The void between stars can reach -270 degrees Celsius, just a few degrees above absolute zero, the theoretical limit where all molecular motion would cease entirely. Yet even this profound chill is warm compared to some places we will visit. Scientists working in specialized laboratories have created conditions colder than anywhere that naturally exists in the known universe. In these carefully controlled environments, matter begins to behave in ways that seem magical, defying our intuitive understanding of how the physical world works. The story of cold is also the story of time. As temperatures drop, processes slow. Chemical reactions that would happen in an instant at room temperature might take millions of years in the deep freeze of interstellar space. In the coldest environments, time itself seems to stretch and dilate, as if the universe were holding its breath. Cold preserves. In the shadowed craters of our Moon and Mercury, scientists believe water ice has remained frozen for billions of years, untouched by the heat of the nearby sun. On more distant worlds like Pluto, exotic ices of methane and nitrogen form landscapes that remain essentially unchanged for eons. Geological processes slowed to a near standstill by the profound cold. There is a special kind of silence that accompanies extreme cold. Sound waves need matter to travel through, and in the vacuum of space, there is nearly nothing to carry them. The coldest places are often the emptiest, creating a silence more complete than anything we can experience on our noisy, vibrant planet. It is a silence that speaks of vast distances and ancient time. As we venture into these frigid realms tonight, we invite you to experience the strange beauty of cosmic winter. There is a stark elegance to these barren landscapes, These slow-moving processes, these places where energy has dwindled to its lowest possible state. Like a perfectly preserved snapshot, the coldest regions of space offer us glimpses into conditions that have remained unchanged since the early universe. The cold also connects us to the deepest questions about our universe's future. Cosmologists tell us that as the eons pass, as stars burn out and galaxies drift apart, the entire cosmos will gradually cool toward a state of uniform chill. The cold we explore tonight may be the ultimate destiny of everything that exists, but that is a future so distant that we need not fear it. For now, we can appreciate the delicate balance that allows us to exist in our warm bubble of life, while marveling at the extraordinary physics that emerges when energy drains away into the void. Prepare yourself for a journey through temperature scales that boggle the mind, through environments more alien than science fiction, through states of matter that exist only in the most extreme conditions. The coldest places in the universe await us. Let us explore them together, with wonder in our hearts and curiosity as our guide. To understand the coldest places in the universe, we must first understand what cold truly means. Our human experience of cold is subjective, a feeling, a sensation against our skin. But in the language of physics, cold has a precise definition, one that takes us to the very foundation of what matter is. Cold is not a thing in itself. It is the absence of heat, and heat, in its most fundamental form, is simply the motion of particles. When you feel warmth, you are feeling the vibration of atoms and molecules as they bounce and collide with increasing energy. To make something cold is to slow this dance, to quiet this vibration, to bring particles closer to perfect stillness. In the vacuum of space, cold behaves differently than it does on Earth. Here on our planet, objects cool primarily through contact with colder substances. A warm cup of tea cools when heat transfers into the cooler air around it. Your body loses heat when touched by cold water or winter wind. This is conduction and convection, the familiar mechanisms of cooling in our daily lives. But in the emptiness of space, there is almost nothing to conduct heat away from an object. No air, no water, no solid matter in significant quantities. Instead, objects in space cool almost exclusively through radiation, the direct emission of energy in the form of infrared light and other electromagnetic waves. This process is slower, more gradual, but ultimately more complete. If you were to float unprotected in the shadow of our planet, far from the warming rays of our sun, your body would slowly radiate its heat into the void. The process would take hours rather than the minutes it might take to freeze in Earth's Arctic waters. But eventually, inexorably, your temperature would approach that of your surroundings, the background temperature of space itself. This background temperature is one of the most remarkable discoveries of modern astronomy. Space is not at absolute zero, as one might intuitively expect. Instead, it maintains a nearly uniform temperature of approximately 2.7 Kelvin, or negative 270.4 degrees Celsius. This slight warmth, this whisper of energy that pervades every corner of the observable universe, is the cosmic microwave background, the fading afterglow of the Big Bang. To truly understand cold in space, we must understand the concept of absolute zero. On the Kelvin scale, used by scientists worldwide, zero marks the theoretical point at which all particle motion would cease entirely. It represents negative 273.15 degrees Celsius, a temperature so profound that the very atoms themselves would nearly stop their quantum jittering. Yet absolute zero remains forever out of reach. The laws of thermodynamics tell us that we can approach this ultimate cold asymptotically, coming ever closer but never quite touching it. Like a mathematical limit, absolute zero is more concept than achievable reality. Even in the deepest regions of space, even in our most advanced laboratories, we can only ever approach this perfect stillness, never fully attain it. The cold of space shapes everything within it. Consider a comet, those frozen wanderers of our solar system. As they approach the sun, their icy surfaces warm, sublimating directly from solid to gas without passing through a liquid phase. This outgassing creates the spectacular tales that have inspired wonder throughout human history. But in the distant reaches of the Oort Cloud, far from our star's warmth, These same comets rest in profound hibernation, their temperatures hovering just above the background radiation of space. Stars themselves exist in a constant battle against the cold. The incredible gravitational pressure at their cores generates the heat necessary for nuclear fusion, the process that lights our night sky. Without this internal furnace, stars would quickly cool and collapse. Indeed, this is exactly what happens when massive stars exhaust their nuclear fuel, leading to the formation of white dwarfs, neutron stars, and black holes, each with its own relationship to temperature and cooling. Time behaves differently in the cold of space. Chemical reactions that occur in fractions of seconds at Earth temperatures might take millions of years in the deep freeze between stars. A hydrogen and oxygen molecule that would eagerly combine to form water in our atmosphere might pass by each other endlessly in the void, lacking the energy to break their existing bonds and form new ones. This chemical sluggishness is why complex molecules can survive in interstellar space for eons, untouched by processes that would quickly transform them on warmer worlds. The experience of cold in space would be unlike anything we feel on Earth. Our bodies sense temperature primarily through the transfer of heat energy, either into or out of our skin. But in the vacuum of space, there is no air or water to carry heat away from your body through convection. Instead, you would lose heat solely through radiation, a much slower process. Paradoxically, overheating can be as much a danger for astronauts as freezing, since their bodies generate heat that cannot easily disperse without the help of air or water. Spacecraft face similar challenges. In direct sunlight, the side of a space station facing the sun might reach temperatures exceeding 120 degrees Celsius, hot enough to boil water. Meanwhile, the shadowed side might plunge to negative 120 degrees Celsius or lower. This extreme temperature gradient occurs across mere meters, creating engineering challenges unique to the space environment. The International Space Station and other human habitats in orbit use elaborate systems of radiators, insulation, and heat distribution to maintain comfortable temperatures for their crews. Without these systems, the metal hull would expand and contract with each orbit, eventually weakening and failing as it passes repeatedly from searing heat to bitter cold. Even light itself is affected by extreme cold. As photons travel through the nearly perfect vacuum of space, they gradually lose energy, their wavelengths stretching into the red and infrared portions of the spectrum. This redshifting is partly why distant galaxies appear red to our telescopes, their light exhausted by the vast journey across expanding space, cooling as the universe itself cools. When astronomers study the coldest regions of space, they often use infrared telescopes, instruments sensitive to the faint heat signatures of objects too cool to emit visible light. These specialized observatories must themselves be cooled to cryogenic temperatures to prevent their own heat from overwhelming the subtle signals they seek to detect. Like looking for a candle in daylight, finding cold objects requires first eliminating all sources of competing warmth. The James Webb Space Telescope, humanity's most advanced infrared observatory, operates at temperatures below 50 Kelvin, maintained by a massive sunshield, and its position far from Earth's reflected heat. This extreme cold allows it to detect the faintest thermal signatures from the earliest galaxies, objects so distant their light has been traveling for more than 13 billion years. Cold affects not just the objects we observe in space, but the very tools we use to observe them. Electronic sensors become more sensitive at low temperatures, with less thermal noise to contaminate their measurements. Superconducting materials, which lose all electrical resistance when sufficiently chilled, enable the most sensitive detectors ever created. In this way, cold becomes not just the subject of our cosmic investigations, but an essential ally in conducting them. Perhaps the most profound aspect of cosmic cold is its relationship to entropy, the tendency of all systems to move from order to disorder. Cold regions represent low entropy states, places where energy is concentrated rather than dispersed. The universe as a whole moves inexorably toward higher entropy, towards states of greater disorder and more evenly distributed energy. In this grand process, the pockets of extreme cold we observe are temporary anomalies, destined to eventually warm as heat energy equalizes across the cosmos. The cold of space also preserves information. In the frozen surfaces of distant moons and planets, in the composition of ancient comets, In the distribution of gas clouds that have remained undisturbed for millions of years, scientists can read the history of our solar system and beyond. Like insects preserved in amber, the cold environments of space offer snapshots of conditions from the distant past, protected from the erasure of time by their profound chill. For humans, venturing into the cold of space requires elaborate technological protection. The spacesuits worn by astronauts during extravehicular activities are marvels of engineering, providing not just air to breathe, but carefully regulated temperature control. Without this protection, exposure to the vacuum would be fatal within minutes, though not from freezing as often depicted in science fiction. Rather, the combination of rapid pressure loss, oxygen deprivation, and radiation exposure would claim life well before the cold itself could fully take hold. As we contemplate the cold of space, we must also consider its profound emptiness. At the boundary of our solar system, in what astronomers call the interstellar medium, there might be only a few atoms per cubic centimeter compared to billions of billions in the air we breathe. This extraordinary sparseness means that even though the temperature may register as just a few Kelvin above absolute zero, an unprotected human would not feel intense cold immediately. There simply aren't enough particles to rapidly conduct heat away from the body. The relationship between cold and life is complex. While extreme cold can preserve biological material for extraordinary periods, it also dramatically slows the chemical reactions necessary for life as we know it. Yet scientists speculate that exotic forms of life might exist in the cold depths of space, perhaps operating on timescales so slow that a single thought might take centuries to form. Such hypothetical organisms would experience the universe very differently than we do, perceiving our frantic warmth-driven activities as an incomprehensible blur. From our warm perspective on Earth, where water flows and chemical reactions proceed at rates conducive to our biology, the cold of space might seem hostile and forbidding. Yet this vast coldness is not an aberration, but the natural state toward which all things trend. Our warm planet, our warm bodies, these are the cosmic exceptions, temporary islands of heat in an ocean of crystalline chill. To feel cold is human, but in space, cold has no feeling. It is the absence of everything. It is the baseline from which all energy rises, the canvas upon which the universe paints its warming exceptions. As we continue our journey to the coldest places in the cosmos, remember that the cold we explore is not just an extreme condition, but the fundamental state from which everything else deviates. The story of heat is the story of exceptions. The story of cold is the story of the rule. Our journey through the coldest places in the universe brings us to a paradoxical beginning. The coldest, most pervasive phenomenon we can observe today was once the hottest event in cosmic history. We speak of the cosmic microwave background, the faint afterglow of the Big Bang itself, now cooled to just above absolute zero by the relentless expansion of space. 13.8 billion years ago, our entire observable universe existed in a state of unimaginable heat and density. In the first fraction of a second after the Big Bang, temperatures soared to trillions of degrees, a cosmic furnace so intense that not even atoms could form. Matter as we understand it could not exist. Instead, a soup of elementary particles and radiation mingled in perfect equilibrium, too energetic to combine into more complex structures. As the universe expanded, this primordial fireball began to cool. After approximately 380,000 years, temperatures had fallen enough for electrons to bind with protons, forming the first neutral hydrogen atoms. This pivotal moment in cosmic history is known as recombination, though the name is somewhat misleading since these particles had never combined before. With this joining of electrons and protons, something remarkable happened. The universe, which until then had been opaque to light, suddenly became transparent. Photons, which had been constantly scattered by free electrons, could now travel unimpeded across space. These liberated light particles form what we now observe as the cosmic microwave background radiation, or CMB. When these photons began their journey, they glowed with the heat of the young universe, roughly 3000 Kelvin, appearing as visible light with a reddish-orange hue, similar to the embers of a dying fire. If human eyes had existed, then to witness this moment, the entire sky would have glowed with this uniform warm light, no stars yet punctuating the cosmic dawn. But as these photons traveled through expanding space, something profound happened to them. The very fabric of the universe stretched, and with it, the wavelengths of this ancient light elongated. What began as visible light slowly shifted through the infrared spectrum and eventually into the microwave region where we detect it today. Now, after traveling for almost the entire history of our universe, these ancient photons have cooled to just 2.7 Kelvin, or negative 270.4 degrees Celsius. This temperature, barely above absolute zero, makes the CMB the second coldest large-scale phenomenon in the natural universe, exceeded in its chill only by a few specialized structures like the Boomerang Nebula, which we will explore later. The discovery of this cosmic background radiation was one of the most significant scientific findings of the 20th century, though it began almost as an accident. In 1964, two radio astronomers at Bell Laboratories, Arno Penzias and Robert Wilson, were testing a sensitive microwave receiver originally designed for satellite communications. They encountered a persistent background noise that seemed to come from all directions of the sky with equal strength. After eliminating all possible terrestrial sources of interference, including the droppings of pigeons nesting in their antenna, Penzias and Wilson realized they had stumbled upon something of cosmic significance. Simultaneously, a team at Princeton University led by Robert Dicker had been specifically searching for this radiation, having predicted its existence based on Big Bang theory. When the two groups connected, they realized that Penzias and Wilson had found the first observational evidence for the Big Bang model of the universe, a discovery that would eventually earn them the Nobel Prize in Physics. What makes the cosmic microwave background so remarkable is its extraordinary uniformity. No matter where we point our detectors, this ancient light appears almost exactly the same temperature, varying by only about 1 part in 100,000. These tiny temperature fluctuations, mere whispers of difference, represent the seeds from which all structure in our universe eventually grew. The slightly denser regions, ever so slightly warmer than their surroundings, became the gravitational anchors around which matter would eventually coalesce to form the first stars and galaxies. Modern observations of the CMB, made by specialized satellites like COBE, WMAP, and Planck, have mapped these minute temperature variations with incredible precision. The resulting images show a cosmic baby picture, a snapshot of our universe when it was just 380,000 years old, less than 1/10,000th of its current age. The patterns we observe in this ancient light have become one of our most important tools for understanding the fundamental parameters of the cosmos, from its age and composition to its geometry and ultimate fate. The cold of the cosmic microwave background tells us something profound about the nature of expansion itself. As the universe stretches, it does not expand into some pre-existing space. Rather, space itself expands, carrying galaxies along like raisins in a rising loaf of bread. This expansion affects not just the distance between galaxies, but the very wavelength of light traveling through this expanding medium. Consider the analogy of a wave drawn on the surface of a balloon. As you inflate the balloon, the wave pattern stretches, its peaks and troughs moving further apart. Similarly, as space expands, the wavelengths of photons traversing it are stretched, a phenomenon known as cosmological redshift. This stretching reduces the energy of each photon, cooling the radiation from its initial searing heat to the frigid whisper we detect today. The current temperature of the CMB serves as a cosmic thermometer, allowing us to measure precisely how much the universe has expanded since the time of recombination. When these photons began their journey, the observable universe was about 1,000 times smaller in each dimension than it is today. This means that every cubic meter of our current space contained what would eventually expand to fill 1 billion cubic meters of our present universe. This expansion continues today, and with it, the cooling of the cosmic background. In another 13 billion years, the temperature of this radiation will have fallen to approximately 1.35 Kelvin, half its current value. As eons pass, it will continue its asymptotic approach toward absolute zero, never quite reaching it, but growing ever colder as the universe stretches toward infinity. There is a profound beauty in the fact that we can still detect this ancient light, this echo of creation. The photons that now register as microwaves in our sophisticated detectors have traveled across nearly the entire observable universe without being absorbed or scattered. They represent the oldest directly observable signal we can detect, a fossil imprinted on the sky itself. The uniformity of the CMB also tells us something fundamental about the early universe. For the temperature to be so consistent in all directions, the entire observable cosmos must have been in thermal equilibrium before inflation, a theorized period of exponential expansion in the earliest moments after the Big Bang. This presents a puzzle, since regions on opposite sides of our sky would not have had time to communicate with each other, even at the speed of light, given the age and size of the observable universe. This conundrum, known as the horizon problem, is one of the key motivations for inflationary theory. If we could somehow strip away all the stars, galaxies, and gas clouds that have formed since the CMB was created, if we could see only this primordial light, the entire sky would glow with a uniform microwave emission, appearing to our instruments as a perfect blackbody radiator at 2.7 Kelvin. This is what astronomers mean when they speak of the temperature of space itself. It is not the temperature of the vacuum, which has no intrinsic temperature, but rather the temperature of this omnipresent radiation field through which everything in our universe moves. For most astronomical objects, the CMB represents a temperature floor, the minimum temperature they can naturally achieve through radiative cooling. A cloud of gas in intergalactic space, far from any star or galaxy, will eventually cool to this background temperature, reaching a state of thermal equilibrium with the cosmic radiation field. To cool something below this temperature requires active refrigeration, the expenditure of energy to pump heat away from the system, something that happens only in specialized natural circumstances or in human laboratories. The story of the cosmic microwave background is also the story of entropy and the arrow of time. In the hot, dense early universe, energy was highly concentrated, a low entropy state analogous to a fully wound spring. As expansion proceeded and the universe cooled, this energy dispersed, increasing the total entropy of the system. The cold CMB we observe today represents a much higher entropy state than the hot plasma that preceded it, consistent with the second law of thermodynamics. Yet paradoxically, while the overall entropy of the universe has increased dramatically since the Big Bang, the expansion of space has also created the conditions for local decreases in entropy, allowing complex structures like galaxies, stars, planets, and ultimately life to form. These organized systems represent temporary islands of order in the ever-growing sea of cosmic disorder, made possible by the background cold of expanding space. There is a certain poetic symmetry in the fact that our warm human bodies, composed of atoms forged in the hearts of stars, now study the cold remnant of the universe's fiery birth. We are, in a very real sense, the universe examining itself, a portion of the cosmos that has organized itself sufficiently to contemplate its own origins and ultimate fate. When we measure the precise spectrum of the cosmic microwave background, we find it matches the theoretical profile of a perfect blackbody radiator with extraordinary accuracy. This perfect match is one of the strongest pieces of evidence supporting the hot Big Bang model of cosmology. Alternative theories struggle to explain how such a precise blackbody spectrum could arise without an early state of extreme heat and density, followed by gradual cooling. The temperature of the CMB also allows us to calculate the density of photons in the universe. On average, there are approximately 400 CMB photons per cubic centimeter throughout all of space. This may not sound like much, but it vastly outnumbers the average density of atoms, which is less than 1 per cubic meter in intergalactic space. By simple count, the universe contains roughly 1 billion photons for every atom of ordinary matter, most of these being the ancient light of the cosmic microwave background. As these photons continue to cool with cosmic expansion, they will eventually become undetectable with any realistic technology. In the far distant future, trillions of years hence, civilizations that might exist then would have no direct observational evidence of the Big Bang or the early universe. The cosmic microwave background will have stretched to wavelengths too long to distinguish from random quantum fluctuations, erasing this crucial piece of cosmological evidence. In this sense, We live in a privileged epoch, still able to directly observe the afterglow of creation before it fades forever into the deepening cold of cosmic night. When we look at detailed maps of the CMB temperature variations, we can see evidence of sound waves that propagated through the early universe. Just as air carries sound waves through pressure variations, the primordial plasma of the early cosmos carried acoustic oscillations, regions of compression and rarefaction that left their imprint on the background radiation. By analyzing the size and distribution of these acoustic patterns, cosmologists can determine the composition of the early universe with remarkable precision, measuring the relative abundances of ordinary matter, and dark energy. Perhaps the most counterintuitive aspect of the CMB is that despite its extreme cold, it actually represents a limit on how cold natural objects in space can become. Any object radiating heat into empty space will eventually cool to this background temperature and then stop cooling further, having reached equilibrium with its surroundings. To cool below the CMB temperature requires something to absorb the background radiation itself, shielding the object from this omnipresent glow. In this way, the cold of the CMB both enables the formation of complex structures and sets a limit on the natural cooling processes of the cosmos. It is both canvas and constraint, both the backdrop against which the cosmic drama unfolds and a fundamental participant in that ongoing story. The precision with which we can measure the CMB temperature has increased dramatically since its discovery. Modern instruments can detect variations as small as a few microkelvin, approximately 1/1,000,000th of a degree. This extraordinary sensitivity allows cosmologists to create detailed maps of the tiny temperature fluctuations across the sky, revealing the faint imprints of various physical processes from the early universe. One of the most remarkable aspects of the CMB is that it contains information from multiple epochs of cosmic history. While the radiation itself originated about 380,000 years after the Big Bang, the pattern of temperature variations we observe carries information from much earlier times, potentially even from the first fractions of a second after the universe began. As these primordial photons traveled toward us, they were also influenced by the large-scale structure that formed later, creating secondary effects that experienced cosmologists can disentangle from the primary signal. The polarization of the CMB photons provides another rich source of information. Just as sunlight can be polarized by scattering off particles in our atmosphere, creating the blue sky, CMB photons became slightly polarized through interactions with electrons during the era of recombination. The exact pattern of this polarization carries unique information about conditions in the early universe, including potential signatures of gravitational waves generated during the inflationary epoch. Scientists studying the CMB must be extraordinarily careful to account for sources of contamination that could affect their measurements. Our own galaxy emits microwave radiation that must be meticulously subtracted from the observations. Even the motion of our solar system through space creates a slight Doppler effect in the CMB, making it appear slightly warmer in the direction we're moving and cooler in the opposite direction. These effects must be removed to reveal the true cosmic signal. The search for particular patterns in the CMB continues to drive advances in observational cosmology. Theorists have predicted that certain types of inflation models would produce specific signatures in the polarization of the CMB, potentially observable with the next generation of detectors. Finding these patterns would not only confirm inflation, but could also provide evidence for physics at energy scales far beyond what any Earthbound particle accelerator could ever achieve. The concept of temperature itself becomes somewhat peculiar when applied to the cosmic background. While we measure it at 2.7 Kelvin today, this doesn't mean that space has a fixed temperature everywhere. Due to the finite speed of light, when we look at distant regions of the universe, we see them as they were in the past. Since the universe is expanding and cooling, if we could somehow instantly transport ourselves to a galaxy billions of light years away, we would measure the local CMB temperature there to be slightly warmer than what we observe from Earth, reflecting an earlier stage in the universe's cooling process. This gradient of temperature across cosmic distances has actually been measured indirectly. When CMB photons pass through the hot gas in galaxy clusters, some of the photons gain energy through interactions with the energetic electrons in this gas. a process known as the Sunyaev-Zeldovich effect. By observing this effect in clusters at different distances from Earth, astronomers have confirmed that the background radiation was indeed warmer in the past, exactly as predicted by the Big Bang model. The pervasive nature of the CMB means that it impacts many aspects of astronomy and cosmology. For instruments operating at millimeter wavelengths, it represents a source of background noise that must be accounted for. For interstellar gas clouds, it provides a source of heating that prevents them from cooling below its temperature. For theoretical physicists, it offers a window into the extreme conditions of the early universe, allowing them to test models of fundamental physics against observational data. The cosmic microwave background also provides one of our best constraints on the total energy content of the universe. By carefully analyzing its patterns, cosmologists have determined that ordinary matter, the stuff of atoms and molecules, makes up only about 5% of the total energy density of the cosmos. The remaining 95% consists of dark matter and dark energy, mysterious components whose nature remains one of the greatest unsolved problems in physics. Looking back at the tremendous heat of the early universe and its subsequent cooling to the frigid temperatures we measure today gives us perspective on our own place in cosmic history. We exist in an intermediate phase, after the searing heat of creation, but before the deep freeze of cosmic old age. Our warm biosphere, our comfortable temperature range, represents a fleeting middle ground in the universe's long journey from fire to ice. As our instruments continue to improve, the CMB will likely yield even more secrets about the birth and evolution of our universe. Ground-based observatories in Antarctica and high-altitude sites in Chile push the boundaries of what we can detect from Earth, while space-based missions offer the ultimate platform for these delicate measurements, free from atmospheric interference. Each generation of instruments reveals new details, new patterns, new clues to the cosmic puzzle. For all its profound cold, the cosmic microwave background represents a connection to the hottest moment in cosmic history. It links us directly to our origins, carrying information across vast gulfs of time and space to tell the story of how everything began. In its subtle patterns, we read the conditions that eventually allowed for our existence, the seeds of all cosmic structure preserved in this ancient, frigid light. As we continue our journey to even colder regions of our universe, keep in mind that we are always moving through this bath of ancient photons, this faint signal from the beginning of time. The cosmic microwave background is not something distant or separate from us. It permeates all of space, passing through our bodies at this very moment, connecting us directly to the infant universe in its earliest moments of existence. Even the light from the birth of the cosmos has dimmed into cold silence. As we continue our journey through the coldest places in the cosmos, we now turn our attention to regions so vast and empty that they challenge our understanding of the universe itself. These are the cosmic voids, enormous bubbles of nearly nothing that punctuate the large-scale structure of space. Here, in these darkest and most desolate regions, cold takes on a different character, born not of active cooling processes, but of profound absence. Imagine floating in a region of space so empty that you could travel for hundreds of millions of light years and encounter almost nothing. No bright galaxies, no warm stars, no drifting clouds of cosmic gas, just emptiness stretching in all directions, a three-dimensional darkness broken only by the occasional lonely galaxy that somehow found itself adrift in this cosmic desert. These are the great voids, and they comprise most of the volume of our universe. When astronomers first began mapping the distribution of galaxies in detail during the 1980s, they expected to find a relatively uniform spread, perhaps with subtle clumping here and there. Instead, they discovered something remarkable. Galaxies are arranged in a vast cosmic web, with dense clusters and filaments surrounded by enormous empty regions. This unexpected structure, often compared to bubbles in a cosmic bath or to the cells of some vast organism, forced scientists to reconsider their models of how the universe evolved after the Big Bang. The largest known void discovered so far spans an almost incomprehensible 1.8 billion light-years across. This region, known as the Bootes void, named after the constellation in which it appears, contains so few galaxies that if our Milky Way were placed at its center, we would not have discovered the existence of other galaxies until the 1960s. Our telescopes simply would not have been powerful enough to detect anything across such enormous empty distances. We would have developed a profoundly different understanding of our place in the cosmos, perhaps believing ourselves to be alone in an otherwise empty universe. The emptiness of these voids affects their temperature in subtle but important ways. With so few galaxies, there are minimal sources of heat energy. No supernova explode to release their thermal energy into the surrounding space. No active galactic nuclei inject high-energy particles. The gas density is so low that even when atoms do collide and heat up, they quickly radiate that energy away without transferring it to other particles. The result is that these vast cosmic voids approach the background temperature of the universe itself. At negative 270.4 degrees Celsius, just 2.7 Kelvin above absolute zero, they are kept from becoming colder only by the omnipresent cosmic microwave background radiation we discussed in the previous chapter. They represent some of the coldest large-scale environments in the natural universe, but their cold is of a peculiar kind. It is not the cold of active cooling like we find in certain specialized astronomical objects. Rather, it is a cold born of absence and distance, of isolation from sources of energy, a default state that emerges when nothing disturbs the quiet background temperature of space. The formation of these enormous voids remains an area of active research in cosmology. The current understanding suggests that they evolved from subtle underdensities in the early universe, regions that were just slightly less dense than their surroundings. While overdense regions attracted more and more matter through gravity, eventually forming the galaxies and clusters we see today, these underdense regions evolved in the opposite direction, giving up their matter to the surrounding regions and becoming progressively emptier over cosmic time. This process, driven by the same gravitational forces that build galaxies, works in reverse in the voids. Matter flows away from these regions rather than toward them, like water draining from high ground. Over billions of years, this gentle but persistent outflow has evacuated the voids, leaving behind vast volumes of space with densities less than 1/10 the cosmic average. What little matter remains in these voids is primarily composed of hydrogen and helium gas, so diffused that it makes the best vacuum we can create in Earth laboratories seem densely packed by comparison. In the most extreme regions of the largest voids, there might be only a few atoms per cubic meter, compared to roughly a billion atoms in a similar volume of air at Earth's surface. This extraordinary emptiness means that particles can travel enormous distances without interacting with anything else, the very definition of a near-perfect vacuum. The cold of the voids is also special because it is remarkably uniform. Without significant sources of heat or activity, the entire void approaches the same background temperature, varying perhaps by tiny fractions of a degree across millions of light years. This uniformity makes them uniquely valuable to cosmologists studying the universe's thermal history, offering a baseline against which other, more dynamic regions can be compared. Despite their emptiness, or perhaps because of it, cosmic voids have become valuable tools for testing theories of gravity and cosmology. The way in which matter has been evacuated from these regions depends sensitively on the laws of gravity and the overall composition of the universe. By carefully measuring the size, shape, and emptiness of voids, scientists can test alternative theories of gravity and constrain the properties of dark energy, the mysterious force driving the accelerating expansion of the universe. Voids also provide a uniquely clear view of the cosmic background radiation. When we look at the CMB through regions occupied by galaxy clusters, the hot gas in these clusters affects the photons passing through, slightly distorting our view of the early universe. But when we look through voids, we see the cosmic background with minimal interference, allowing for more precise measurements of its properties. This pristine view has led to the discovery of particularly cold spots in the cosmic microwave background, regions where the temperature dips slightly below the average of 2.7 Kelvin. The most famous of these, known simply as the CMB cold spot, appears in the constellation Eridanus and has a temperature approximately 70 microkelvin cooler than its surroundings. A tiny but significant difference that has generated considerable scientific interest. Some researchers have suggested that this cold spot might be the result of a particularly large void along our line of sight, its subtle gravitational effects cooling the photons that pass through it. Others have proposed more exotic explanations, including the possibility that it represents evidence of our universe colliding with another in the distant past, a cosmic bruise from a multiversal encounter. While such speculative ideas remain unproven, they highlight how the cold, empty regions of our universe continue to inspire scientific creativity and wonder. The boundaries where voids meet the filaments and clusters of the cosmic web are regions of particular interest. Here, the temperature begins to rise as gas flows into denser regions and becomes compressed. These void boundaries, sometimes called cosmic watersheds because they resemble the ridgelines that separate water flowing into different river basins, represent the transition from the cold emptiness of the voids to the relatively warmer environment of the cosmic web. The few galaxies that do exist within the great voids are fascinating objects in their own right. Unlike their counterparts in denser regions, void galaxies have evolved in isolation, free from the interactions and mergers that shape galaxies in clusters. They tend to be bluer, indicating active star formation, and more diffuse in their structure. Like rare flowers in a desert, they have adapted to their barren environment, finding ways to continue forming stars despite the scarcity of gas in their surroundings. These void galaxies also tend to be smaller than average, suggesting that the largest galaxies can only form in regions where there is sufficient matter density for multiple galactic mergers to occur. In the emptiness of the voids, such encounters are exceedingly rare, limiting the growth potential of the galaxies that form there. It is as if these cosmic hermits have chosen solitude over the community that would allow them to grow larger. The largest voids are not completely empty, not absolute vacuums in the strict sense. They contain not only the occasional galaxy and diffuse gas, but also dark matter, the invisible substance that makes up approximately 27% of the universe's energy content. However, even this dark matter is less concentrated in voids than elsewhere, having followed the same gravitational evolution as ordinary matter, flowing away from underdense regions toward the filaments and clusters that surround them. This evacuation of dark matter creates a distinctive gravitational signature that astronomers can detect through its effects on light passing through and around voids. As photons travel through regions with less mass, they experience slightly less gravitational lensing, the bending of light by matter. By carefully measuring this effect, scientists can map the distribution of dark matter in and around voids, confirming that it too avoids these cosmic deserts. The emptiness of voids affects not just their temperature, but also their chemistry. Chemical reactions require particles to encounter each other, something that happens far less frequently in the extreme vacuum of void regions. As a result, the gas in voids remains primarily in its primordial state, composed almost entirely of hydrogen and helium, with minimal contamination from heavier elements. It is like a preserved sample of the early universe, unchanged by the nuclear fusion processes that have enriched matter in denser regions. This chemical purity makes void gas valuable for certain types of cosmological measurements. By observing the absorption lines of this gas against background quasars, astronomers can probe the physical conditions in the void with extraordinary precision, measuring not just its density, but also its temperature and ionization state. These observations reveal that much of the gas in voids is actually quite warm, heated by ultraviolet radiation from distant galaxies and quasars to temperatures of tens of thousands of degrees. This might seem contradictory, given our focus on voids as cold places. But temperature in the context of diffuse gas refers to the average energy of individual particles, not the total heat content of a region. A cubic meter of void gas might contain just a few thousand atoms, each moving quite rapidly, giving it a high temperature in the technical sense. Yet the total thermal energy contained in that cubic meter would be extraordinarily low because there are so few particles. It is a subtle distinction, but an important one for understanding the thermal state of the universe's most empty regions. Despite this technicality, the voids remain fundamentally cold places in terms of their overall energy content and their distance from thermal equilibrium. They are regions where entropy has already approached its maximum, where the dissipation of energy has run its course, leaving behind a sparse, rarefied medium that will likely grow only colder and emptier as the universe continues to expand. Looking toward the distant future, Cosmologists predict that the voids will continue to grow larger and emptier as the expansion of the universe accelerates. Galaxies on the edges of voids will be drawn further away by the cosmic flow, and the few galaxies within voids will eventually exhaust their gas supplies and cease forming new stars. In the very distant future, trillions of years hence, these void galaxies will fade to darkness as their stars burn out, leaving behind truly empty regions where once there was at least some faint light. This ongoing evacuation of the voids is part of a larger process that cosmologists call the cosmic web evolution. Over time, the web becomes increasingly pronounced, with denser filaments and clusters separated by larger and emptier voids. It is as if the universe is crystallizing, separating into distinct phases of high and low density in a process that will continue for the foreseeable cosmic future. The rate at which voids empty depends on the overall fate of the universe, which in turn depends on the nature of dark energy, the mysterious force driving cosmic acceleration. If dark energy maintains its current properties, the voids will continue to expand and empty indefinitely. But if dark energy changes over time, becoming stronger or weaker, the future evolution of voids could follow a different trajectory, potentially even reversing if the universe were to begin contracting in a so-called Big Crunch scenario. For now, though, the voids continue their quiet emptying, growing colder and darker with each passing eon. They represent a preview of the universe's distant future, when expansion will have driven all galaxies outside each other's observable horizons, leaving behind what appears to be an empty void for any observers who might still exist. In studying today's voids, we glimpse not just the coldest environments of the present cosmos, but also the ultimate fate of space itself. There is a profound silence to these void regions, not just the absence of sound, which cannot propagate through the vacuum of space regardless of location, but a deeper quiet. No supernovae explosions disturb the darkness. No colliding galaxies send gravitational waves rippling through space-time. No new stars ignite to push back against the encroaching night. It is a silence of events, of happenings, of the processes that elsewhere drive cosmic evolution. Yet even in this stillness, subtle processes continue. The rare atoms that drift through the void occasionally encounter a photon from the cosmic background or from a distant galaxy, absorbing energy and then re-emitting it in a different direction. These extraordinarily rare interactions, occurring perhaps once in thousands of years for a given atom, represent the minimum of activity possible in our universe, the baseline metabolism of empty space. The cold of the voids teaches us something important about the nature of temperature itself. We tend to think of hot and cold as absolute properties, but they are fundamentally relative concepts, meaningful only in comparison. The voids are cold compared to the interiors of stars or the centers of galaxy clusters, but they are warm compared to the artificially created states we will explore later in our journey, where temperatures plunge to within billionths of a degree above absolute zero. This relativity of temperature mirrors the relativity of emptiness. The voids are extraordinarily empty by astronomical standards, containing less than 10% of the average cosmic density of matter. Yet compared to the perfect vacuum theorized by quantum field theory, they are positively crowded. The vacuum of space, even in the emptiest voids, teems with virtual particles popping in and out of existence, with quantum fields extending through every point, with the omnipresent dark energy that permeates all of space. These subtleties remind us that the universe resists simple categorization. The boundaries between empty and full, between hot and cold, between active and quiet, are never absolute. They exist on a continuum where each comparison depends on our frame of reference, on what we choose as our baseline. For human observers, accustomed to the warm density of Earth's surface, the void regions represent an environment so alien that we struggle to truly comprehend it. The cold and emptiness would be instantly fatal without extensive technological protection. Yet from the perspective of fundamental physics, these regions are in many ways the most natural state of the universe, the default condition toward which all regions evolve in the absence of concentrating forces. As our journey through the coldest places in the universe continues, we will encounter environments that are technically colder than the cosmic voids. But few can match them for the purity of their cold, for the vastness of their emptiness, for the profound quiet that pervades their enormous volumes. they represent cosmic winter on its grandest scale, a chill that extends not for kilometers or even light years, but for hundreds of millions of light years in all directions. The voids remind us that most of the universe is empty space, that the bright galaxies and stars that capture our attention are like rare islands in a vast, dark ocean. When we look up at the night sky, our eyes are naturally drawn to the light, to the places where matter and energy have concentrated to push back against the cold of space. But between those lights lies the truer face of the cosmos, the darkness and cold that predominate in the universe's vast empty quarters. Here, between everything, is almost nothing, and that nothing is colder than any place we know. Our journey through the coldest places in the universe now brings us from the vast emptiness of cosmic voids to a much more contained yet equally fascinating environment. Here, in the constellation Centaurus, approximately 5,000 light-years from Earth, lies a dying star surrounded by an expanding shell of gas and dust. This object, known as the Boomerang Nebula, holds a remarkable distinction. It is the coldest natural object ever discovered, with temperatures reaching an astonishing 1 degree Kelvin or negative 272 degrees Celsius. This extreme cold makes the Boomerang Nebula colder than even the cosmic microwave background radiation that pervades all of space. It stands as a cosmic anomaly, a place where natural processes have produced conditions more frigid than the background temperature of the universe itself. To understand how such extraordinary cold can exist, we must explore the fascinating physics of dying stars and expanding gases. The story of the Boomerang Nebula begins, as do all stellar tales, with gravity. Billions of years ago, a star similar to our Sun formed from a collapsing cloud of gas and dust. For most of its life, this star burned steadily, fusing hydrogen into helium in its core, balancing the inward pull of gravity with the outward pressure of nuclear fusion. But as stars age, this balance cannot last forever. When a star like our Sun exhausts the hydrogen in its core, it begins to fuse helium instead, becoming a red giant in the process. The outer layers expand dramatically, cooling as they stretch outward. Eventually, these outer layers are expelled entirely, creating what astronomers call a planetary nebula, though these objects have nothing to do with planets. Rather, the name comes from their often round appearance when viewed through early telescopes. The Boomerang Nebula represents a particular type of planetary nebula, one still in the process of forming. What makes it unique is the extraordinary speed with which its outer layers are being expelled. Gas is streaming away from the dying central star at velocities approaching 164 kilometers per second, creating a rapid expansion that directly leads to its record-setting cold. To understand why expansion creates cold, we need to consider one of the fundamental principles of thermodynamics. When a gas expands quickly without gaining heat from its surroundings, it cools. This process, known as adiabatic expansion, is the same principle that makes the air from an aerosol can feel cold or creates the visible cloud when you exhale on a frigid winter morning. In the Boomerang Nebula, this principle operates on a cosmic scale. As the expelled gas rushes outward, it expands rapidly into the surrounding space. This expansion causes the gas to cool dramatically, similar to how a refrigerator works, but without the mechanical compressor. The gas does work against its own internal pressure as it expands, converting thermal energy into the energy of expansion and leaving behind less heat. What makes the Boomerang Nebula special is the extraordinary rate of this expansion. Most planetary nebulae expand more slowly, allowing radiation from the central star or from nearby stars to warm the expanding gas. But in the Boomerang, the expansion is so rapid and efficient that it overwhelms all sources of heating, allowing temperatures to plunge below even the cosmic background. When astronomers first discovered this object in 1980, they noted its peculiar shape, which in early observations resembled a boomerang, giving the nebula its distinctive name. Later, more detailed observations revealed that the apparent boomerang shape was actually just the waist of a much larger hourglass or bow tie-shaped structure. This shape offers important clues about the nebula's history and the causes of its extreme cold. The hourglass structure suggests that the star's mass loss is not uniform in all directions. Instead, it appears that something has constricted the outflow along the equator of the system, forcing the expelled gas to stream out more rapidly along the poles. This constriction might be caused by a companion star or even a giant planet orbiting the dying central star, its gravity shaping the outflow into the distinctive form we observe. This asymmetrical expansion creates regions of particularly rapid cooling, especially along the polar axes, where the gas expands most freely. It is in these regions that astronomers have measured the record-setting cold, though the entire nebula exists at temperatures far below anything we experience on Earth. The Atacama Large Millimeter Array, a sophisticated radio telescope in the high desert of Chile, has provided our most detailed observations of the Boomerang Nebula. These observations reveal not just the extreme cold, but also the complex structure of the expanding gas. The nebula consists of multiple layers, each representing a different episode of mass loss from the central star, each with its own temperature profile and chemical composition. What makes these observations particularly challenging is that the nebula is absorbing radiation from the cosmic microwave background itself. This absorption occurs because the gas in the nebula is actually colder than the background radiation, a situation that reverses the usual relationship between astronomical objects and the CMB. Instead of standing out as a warm object against the cold background of space, the boomerang appears as a cold shadow against the slightly warmer cosmic radiation field. This unusual situation allows astronomers to directly measure the temperature of the nebula by analyzing how much CMB radiation it absorbs. The results confirm that large regions of the nebula exist at temperatures below 2.7 Kelvin, with the coldest areas approaching 1 Kelvin. These measurements make the Boomerang Nebula the coldest known natural object in the universe, colder than any planet, moon, or interstellar cloud yet discovered. The extreme cold of the Boomerang Nebula is not permanent, however. As the expelled gas continues to expand, it will eventually become so diffuse that it can no longer cool efficiently. At the same time, radiation from the central star and from the interstellar medium will begin to warm the gas. Over thousands of years, the temperature will gradually rise, eventually equilibrating with the cosmic microwave background. The nebula's record-setting cold is a transient phase in its evolution, a brief window in cosmic time when we can observe this extraordinary phenomenon. The central star itself, having shed its outer layers, is also evolving rapidly. Currently, it remains hidden within the thick dust of the nebula, invisible to optical telescopes. But as the nebula continues to expand and thin, this star will eventually become visible as a hot, compact object known as a white dwarf. This stellar remnant, composed primarily of carbon and oxygen, will slowly cool over billions of years, but never reaching the extreme cold of the surrounding nebula during its expansion phase. What makes the Boomerang Nebula particularly valuable to astronomers is that it represents a brief and rarely observed stage in stellar evolution. Most planetary nebulae are discovered after they have already expanded significantly, warming to temperatures well above the cosmic background. The Boomerang offers a glimpse of the earliest stages of planetary nebula formation, a cosmic snapshot of a process that usually evades detection until later phases. The chemistry occurring within this frigid environment is also of great interest to scientists. At such low temperatures, chemical reactions that would proceed rapidly under normal conditions slow to a near standstill. Molecules that would be unstable in warmer environments can persist for extended periods. This makes the Boomerang Nebula a natural laboratory for studying the behavior of matter under extreme conditions, offering insights that complement the controlled experiments conducted in Earth-based laboratories. Among the molecules detected in the Boomerang Nebula are carbon monoxide, hydrogen cyanide, and various other organic compounds. These molecules form in the cool outer layers of the dying star and are then expelled into the expanding nebula, where the extreme cold preserves them from the decomposition they would experience in warmer environments. By studying these preserved molecules, astronomers can learn about the chemical processes occurring inside the star before its outer layers were expelled. The presence of these complex molecules in the outflow from dying stars, like the one at the center of the Boomerang Nebula, has broader implications for astrochemistry and astrobiology. Such stars, the interstellar medium with complex carbon-based molecules, the building blocks from which new stars and potentially habitable planets will eventually form. In this way, the cold nebula participates in a cosmic recycling process, its material destined to become part of future stellar systems. From our perspective on Earth, The Boomerang Nebula appears small and faint, visible only through powerful telescopes. If we could somehow visit this extraordinary object, however, we would find ourselves surrounded by an ethereal cloud of gas and dust lit by the faint glow of the hidden central star. The extreme cold would be imperceptible to our human senses, already overwhelmed by the vacuum of space, but our instruments would register temperatures far below anything naturally occurring on Earth. The nebula extends over about 3 light years, a distance that seems vast by human standards, but is relatively compact in astronomical terms. Within this volume, the temperature varies considerably, with the coldest regions concentrated along the polar outflows, where the expansion is most rapid. These temperature variations create a complex thermal structure that astronomers are still working to fully map and understand. One of the most intriguing aspects of the Boomerang Nebula is its implications for our understanding of stellar evolution. Most stars in our galaxy with masses similar to the Sun will eventually pass through a phase similar to what we're observing in the Boomerang. Our own Sun, roughly 5 billion years from now, will expand into a red giant before shedding its outer layers to form a planetary nebula. While the details will differ, the basic process will be the same, making the Boomerang a preview of our solar system's distant future. The extreme cold of the Boomerang Nebula also serves as a reminder of the extraordinary range of conditions that exist in our universe. From the searing heat of stellar interiors, where temperatures reach millions of degrees, to the frigid chill of expanding nebulae like the Boomerang, the cosmos encompasses temperature variations far greater than anything we experience in our daily lives on Earth. This vast range of natural temperatures reflects the dynamic nature of the universe, with gravity pulling matter together to create hot, dense objects like stars, while expansion drives matter apart, creating cold, diffuse regions like the Boomerang Nebula. These opposing forces, concentration and dissipation, create the rich variety of environments we observe throughout the cosmos. What makes the Boomerang Nebula particularly special is that it represents an extreme case of dissipation, where the expansion is occurring so rapidly that it drives temperatures below even the cosmic background. This makes it not just quantitatively colder than other natural objects, but qualitatively different, capable of absorbing background radiation rather than just emitting less of it. This ability to cool below the background temperature requires specific conditions that are rarely met in the universe. The expansion must be not only rapid, but also optically thick, meaning that the expelled gas must be dense enough to block radiation that would otherwise warm it. The Boomerang Nebula meets these conditions, creating a unique environment that has no close analogues elsewhere in the natural cosmos. The discovery of such extreme cold in the Boomerang Nebula raised immediate questions about whether other similar objects might exist, undetected, elsewhere in our galaxy. Astronomers have searched for other ultra-cold nebulae, but have so far found none that match the Boomerang's extreme temperatures. This suggests that the Boomerang represents a rare and possibly unique phase in stellar evolution, one that few objects occupy at any given time. The rarity of objects like the Boomerang Nebula makes it all the more valuable as a target for astronomical study. It offers a glimpse of physical processes and conditions that cannot be observed elsewhere, a natural experiment in the behavior of matter at temperatures approaching absolute zero. By studying this extraordinary object, scientists gain insights not just into stellar evolution, but into the fundamental physics of ultra-cold gases. The story of the Boomerang Nebula is also a testament to the power of modern astronomical instruments. Its extreme cold was not discovered until the 1990s, when sufficiently sensitive millimeter wave telescopes became available. As our observational capabilities continue to improve, we may yet discover other extraordinary objects that challenge our understanding of what is naturally possible in the cosmos. For now, though, the Boomerang Nebula retains its title as the coldest known natural object in the universe. Its temperature of 1 Kelvin, achieved through the rapid expansion of expelled stellar material, represents a natural minimum that may be approached but not exceeded by other astronomical objects. To find temperatures lower than those in the Boomerang, we must turn to human-made environments, where sophisticated techniques allow scientists to approach ever closer to absolute zero. The physical processes that create such extreme cold in the Boomerang Nebula depend on a delicate balance of factors. The rate of expansion must be rapid enough to cause significant cooling through adiabatic processes, but the gas must also be sufficiently insulated from external heating sources. This insulation comes partly from the nebula's own dust, which shields the inner regions from the warming radiation of neighboring stars. Astronomers believe that the Boomerang Nebula may have entered this ultra-cold phase relatively recently in astronomical terms, perhaps just within the last 1,000 years or so. This timing would explain why it appears to be unique, as we are observing it during a brief transitional stage that few nebulae occupy at any given time. In a few thousand more years, it will likely warm to temperatures more typical of planetary nebulae, losing its special status as the coldest known natural object. The extreme cold in the Boomerang also affects the state of the dust particles scattered throughout the nebula. At temperatures approaching 1 Kelvin, the surface chemistry of these tiny grains changes significantly. Atoms and molecules that collide with the grains tend to stick rather than bounce off, gradually building up icy mantles around each dust particle. These ice-covered grains have distinctive optical properties that astronomers can detect through careful spectroscopic observations. The interaction between dust, gas, and radiation in such an extremely cold environment creates unique spectral signatures that can be observed from Earth. These signatures include distinctive absorption lines in the microwave and far-infrared portions of the spectrum, where the cold molecules in the nebula absorb specific wavelengths of the cosmic background radiation passing through them. When viewed through the Hubble Space Telescope, the Boomerang Nebula displays beautiful and intricate structures that hint at its complex formation history. Concentric shells of material suggest that the central star has undergone multiple episodes of mass loss, each creating its own expanding layer within the overall nebula. These layers interact with each other and with the surrounding interstellar medium, creating shockwaves and turbulence that further shape the nebula's evolution. The cold of the Boomerang Nebula also preserves a kind of astronomical time capsule. The molecules expelled from the dying star carry information about the nuclear processes that occurred within its core, information that would be lost if these molecules were heated and broken apart. By studying this preserved chemical record, astronomers can piece together the life history of the star, determining its original mass, composition, and evolutionary path. This scientific value extends beyond stellar astronomy to our understanding of molecular evolution in space. The complex organic molecules preserved in the cold nebula may represent important steps in the chemical pathways that eventually lead to the building blocks of life. By studying these preserved molecules, astrobiologists gain insights into the cosmic origins of the chemical precursors to life as we know it. The Boomerang Nebula will not remain as we see it today. Over the coming millennia, its expanding gas will continue to thin and gradually warm. The central star will emerge from its dusty shroud, ionizing the surrounding gas with its intense ultraviolet radiation and transforming the cold, neutral nebula into a glowing, ionized one. The current record cold phase represents just a brief moment in the long afterlife of a sun-like star. In this sense, the Boomerang offers us not just a spatial extreme, the coldest natural place known, but also a temporal one, a fleeting phase in stellar evolution that we are fortunate to observe during our brief human window on the cosmos. Like a rare celestial flower that blooms only briefly, the ultra-cold phase of this nebula gives us a glimpse of a transient but extraordinary natural phenomenon. As we contemplate this dying star and its extraordinarily cold shroud, we might reflect on the poetry of its existence. Here, in the death throes of a star not unlike our sun, nature has created conditions colder than the background of space itself. The processes that once generated the warmth and light of a main sequence star now produce their opposite, an expanding cloud of frigid gas that absorbs what little warmth surrounds it. There is a certain symmetry to this transition, a balance to the cosmic equation. What begins in the gravitational concentration of interstellar gas, heating as it contracts to form a star, ends in the dissipation of that same material, cooling as it expands back into the interstellar medium. The cycle from warm to cold, from concentrated to diffuse, represents one of the fundamental rhythms of cosmic evolution. The Boomerang Nebula, with its record-setting cold, reminds us that endings can be as extraordinary as beginnings. A star dying slowly becomes the coldest natural place in all the known universe. Our cosmic journey now takes us to the vast regions that lie between the stars. the interstellar medium that fills the seemingly empty spaces of our galaxy. While not as cold as the exceptional Boomerang Nebula we just explored, these immense regions represent some of the most extensive cold environments in the universe, areas where temperatures routinely hover between 10 and 20 Kelvin, far below any natural cold found on Earth. The interstellar medium is far from the perfect vacuum that early astronomers once imagined. Rather, it is a dilute but complex mixture of gas and microscopic dust particles spread throughout the volume of the galaxy. This material, though incredibly tenuous by earthly standards, plays a crucial role in the life cycle of stars and the overall evolution of galaxies. To appreciate the nature of this cold interstellar environment, we must first understand its composition. About 99% of the interstellar medium consists of gas, primarily hydrogen in various forms. This hydrogen exists in three main states, depending on the local conditions. In the coldest, densest regions, we find molecular hydrogen, where two hydrogen atoms bond together to form molecules. In slightly warmer areas, we find neutral atomic hydrogen, single atoms that have not been ionized. And in regions heated by nearby stars, we find ionized hydrogen, where the electron has been stripped from the atom, leaving behind a positively charged proton. The remaining 1% of the interstellar medium consists of tiny dust grains, typically less than a micrometer in size. These dust particles, composed primarily of carbon, silicon, oxygen, and other elements, may seem insignificant due to their small total mass. However, they play a disproportionately important role in the thermal properties and chemistry of interstellar space. When we look up at the night sky, the evidence of this interstellar material is visible in the dark patches that obscure our view of distant stars, particularly along the plane of the Milky Way. These dark nebulae, such as the famous coal sack in the southern constellation Crux, are regions where dust is especially concentrated, blocking the light from stars behind them. The cold temperatures of interstellar space result from the fundamental balance between heating and cooling processes. In the absence of nearby stars, the main source of heating is cosmic rays, high-energy particles that originate from supernova explosions and other energetic events throughout the galaxy. These particles penetrate deep into even the densest clouds, providing a baseline level of energy input. Cooling, on the other hand, occurs primarily through radiation. Atoms and molecules in the interstellar medium can become excited through collisions with other particles or by absorbing photons. When they return to lower energy states, they emit radiation, effectively converting kinetic energy into photons that can escape from the cloud. This radiative cooling is remarkably efficient in the thin environment of space, allowing temperatures to drop far below anything we experience on Earth. The coldest regions of the interstellar medium are found within dense molecular clouds, sometimes called giant molecular clouds when they reach truly enormous sizes. These clouds, composed primarily of molecular hydrogen along with various other molecules and dust, can span hundreds of light years and contain enough material to form thousands or even millions of stars. Despite their vast size, these molecular clouds remain hidden from optical telescopes, invisible to human eyes. This is because the dust they contain blocks visible light, both from external stars trying to shine in and from any emissions within the cloud trying to shine out. To study these cold, dark regions, astronomers must use radio telescopes, which can detect the emission from molecules like carbon monoxide that accompany the more abundant but harder to observe hydrogen. The interior of a dense molecular cloud is one of the most isolated environments in the galaxy. Shielded from the heating effects of starlight by layers of dust, these regions cool to temperatures of around 10 Kelvin, or negative 263 degrees Celsius. At these temperatures, most molecular species that would be gases on Earth freeze out onto the surfaces of dust grains, forming thin, icy mantles. These icy dust grains become miniature chemical laboratories where atoms and molecules can meet and react on their surfaces. The dust provides a platform that brings reactive species together and in some cases lowers the energy barriers to their combination. This dust grain chemistry is responsible for the formation of many of the complex molecules observed in interstellar space, including some organic compounds that are precursors to the chemistry of life. The interstellar medium is not uniform in its coldness. Rather, it exhibits a complex structure with significant temperature variations over different scales. Astronomers classify the interstellar medium into several distinct phases based on temperature and density. The cold neutral medium, with temperatures around 100 Kelvin, occupies about 1 to 5% of the interstellar volume. The warm neutral medium, at about 8,000 Kelvin, fills about 30 to 60%. The hot ionized medium, heated to millions of degrees by supernova explosions, occupies much of the remaining volume, but contains relatively little mass due to its extremely low density. The coldest phase, the dense molecular clouds we have been discussing, occupies less than 1% of the volume, but contains a significant fraction of the total mass of the interstellar medium. These cold clouds are not distributed uniformly throughout the galaxy, but tend to concentrate along the spiral arms, where the increased density facilitates their formation and shields them from disruptive forces. The boundaries between these different phases of the interstellar medium are not sharp, but rather consist of transition regions where temperature and density gradually change. These interfaces can be especially interesting from a chemical perspective, as they bring together species that typically exist in different environments, enabling reactions that would not occur in either the cold or warm phases alone. Within the coldest regions of molecular clouds, the near absence of heat energy leads to chemical and physical processes that would seem exotic on Earth. Most notably, quantum mechanical effects begin to play a more prominent role as thermal motion decreases. The wave-like nature of particles becomes more evident, and phenomena like quantum tunneling, where particles can pass through energy barriers that classical physics would deem impenetrable, become increasingly important in driving chemical reactions. One of the most significant consequences of the cold in these regions is its effect on star formation. Gravity constantly works to collapse portions of molecular clouds inward, potentially leading to the formation of new stars. However, various forms of pressure, including thermal pressure from the motion of particles, work against this collapse. In warmer regions, the higher thermal pressure can prevent gravitational collapse, except in the densest areas. But in the cold depths of molecular clouds, thermal pressure is minimal, allowing gravity to more effectively compress the material. This is why stars tend to form within the coldest regions of the interstellar medium. The reduced thermal pressure allows gravity to dominate more easily, initiating the collapse that eventually leads to starbirth. Paradoxically, in these icy nurseries, stars begin to stir, their formation processes ultimately converting the cold, diffuse gas into hot, dense stellar cores. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, has revolutionized our ability to peer into these cold, dusty regions. Where visible light telescopes show only dark, obscuring patches, the Webb telescope reveals the intricate structures within molecular clouds, including filaments, clumps, and protostars in various stages of formation. These observations confirm that the cold interstellar medium is far from featureless, but rather contains complex structures shaped by gravity, turbulence, magnetic fields, and stellar feedback. The coldest regions of interstellar space also serve as cosmic refrigerators, preserving molecules that would quickly dissociate in warmer environments. Some of these molecules have been found to be surprisingly complex. Astronomers have detected amino acids, the building blocks of proteins, as well as sugars and other organic compounds essential to life as we know it. The cold temperatures prevent these delicate molecules from breaking apart, allowing them to persist and potentially be incorporated into newly forming planetary systems. This preservation effect has profound implications for the origins of life. The complex organic molecules found in interstellar clouds could be delivered to young planets through comets and meteorites, providing some of the chemical precursors needed for biology to emerge. In this way, the cold of interstellar space may have played an essential role in seeding the early Earth with the compounds that eventually led to life. The dust in these cold regions also plays a crucial role in the formation of molecular hydrogen, the most abundant molecule in the universe. Hydrogen atoms cannot easily combine directly in the gas phase because they need to release energy when forming a bond, and with no third particle to carry away this energy, the newly formed molecule would simply dissociate again. However, on the surface of a dust grain, the excess energy can be absorbed by the grain itself, allowing stable hydrogen molecules to form. Without this dust-facilitated process, molecular clouds as we know them could not exist, and star formation would proceed very differently, if at all. The darkness of molecular clouds caused by their dust content creates a feedback loop that enhances their coldness. As dust absorbs the warming radiation from nearby stars, the interior of the cloud becomes more shielded and thus colder. This increased cold allows more gas to condense onto dust grains, potentially forming larger grains that are even more effective at blocking light. This process can continue until disturbed by some external force, such as the shockwave from a nearby supernova or the radiation from a newly formed star within the cloud itself. Some of the largest and coldest molecular clouds in our galaxy have become familiar objects to astronomers, despite being invisible to the naked eye. The Orion molecular cloud, associated with the visible Orion Nebula, spans hundreds of light years and contains enough material to form thousands of stars like our Sun. The Taurus molecular cloud, a relatively nearby star-forming region, displays intricate filamentary structures that channel gas toward growing protostars. These vast cold regions serve as the stellar nurseries of our galaxy, the birthplaces of future suns. The coldest portions of these clouds, where temperatures approach 10 Kelvin, are particularly associated with the earliest stages of star formation. Here, dense cores of material begin to contract under their own gravity, initiating the long process that will eventually result in nuclear fusion and the birth of a new star. Astronomers can identify these pre-stellar cores by their cold, dense nature, often appearing as dark globules against the already dark background of the molecular cloud when observed at certain wavelengths. As these cores contract, they actually begin to heat up in their very centers, even as the outer regions remain extremely cold. This creates a temperature gradient that drives complex chemistry, as different reactions become possible at different distances from the warming center. The result is a layered structure of molecular species, with some molecules being destroyed in the warmer interior while forming for the first time in the cold outer regions. This chemical differentiation provides astronomers with a clock of sorts, allowing them to estimate the age and evolutionary stage of forming stellar systems. The extreme cold of interstellar space affects not just the chemistry, but also the physics of the gas and dust. In particular, the dust grains can become aligned with the magnetic fields that permeate the interstellar medium, creating a slight polarization of the light that passes through these regions. By measuring this polarization, astronomers can map the structure of magnetic fields within molecular clouds, revealing their crucial role in regulating star formation by providing additional support against gravitational collapse. The cold also leads to a fascinating quantum mechanical effect called depletion. At very low temperatures, certain isotopes of hydrogen, particularly deuterium, can replace normal hydrogen in molecules because the heavier deuterium has slightly lower zero-point energy, making such substitutions energetically favorable. This leads to an enhancement of deuterated molecules in the coldest regions, sometimes by factors of thousands compared to the overall deuterium abundance. Astronomers use this deuterium enrichment as another thermometer to identify the coldest regions of molecular clouds. The surfaces of dust grains in these cold environments develop complex structures of ice, primarily water ice, but also containing frozen carbon dioxide, methane, ammonia, and other volatile compounds. These icy mantles can grow to be quite thick relative to the size of the dust grain itself, effectively doubling or tripling its diameter. The layered structure of these ices, with different compounds freezing out at different temperatures, provides a record of the thermal history of the dust grain and its surroundings. When light from background stars passes through these cold, dusty regions, specific wavelengths are absorbed by the various ice components, creating distinctive spectral signatures that astronomers can detect. By analyzing these absorption features, scientists can determine not just the composition of the ices, but also their structure, whether they are crystalline or amorphous, providing clues to the temperature history of the region. The coldest interstellar environments also showcase another quantum mechanical effect, the behavior of spin isomers. Molecules like hydrogen can exist in different nuclear spin states, known as ortho and para forms, which have slightly different energy levels. At the extremely low temperatures of dense clouds, the conversion between these forms proceeds very slowly, creating non-equilibrium ratios that can persist for millions of years. These ratios provide yet another tool for astronomers to probe the thermal history and age of molecular clouds. As we move through different regions of our galaxy, the temperature of interstellar space varies considerably. In the spiral arms, where star formation is active and many hot, massive stars inject energy into their surroundings. The average temperature of the interstellar medium tends to be higher. In contrast, in the regions between spiral arms, where fewer stars form and less energy is available, the interstellar medium can reach its coldest states. This creates a temperature structure that mirrors the visible structure of the galaxy itself. The cold of interstellar space persists despite numerous heating processes that continuously add energy to the system. Stellar winds, ultraviolet radiation, cosmic rays, and shock waves from supernova all work to heat the interstellar medium. That it remains cold despite these inputs testifies to the extraordinary efficiency of radiative cooling in the vacuum of space, where the sparse distribution of matter allows photons to escape easily, carrying thermal energy away with them. The relationship between the cold interstellar medium and the hot stars that eventually form within it represents one of the fundamental cycles of galactic evolution. Cold gas collapses to form stars, which then heat their surroundings through radiation and stellar winds. This heating can trigger further star formation in adjacent regions while simultaneously dispersing the remaining cold gas, eventually shutting down the star formation process until the gas can cool again. This delicate balance of heating and cooling regulates the star formation rate of the entire galaxy. When we observe distant galaxies, the presence of cold interstellar material is often evident from the dust lanes that cross their spiral arms. These dark bands, visible even from millions of light years away, mark the regions where new stars are likely forming within cold molecular clouds. The balance between this cold material and the hot ionized gas created by star formation activity helps determine whether a galaxy appears as a vibrant, star-forming spiral or a quieter, more evolved system. The cold of interstellar space also manifests in the microwave and radio emission that astronomers detect from molecules within molecular clouds. Many molecules emit radiation when they change rotational states, transitions that occur at the low energy levels corresponding to these cold environments. By mapping this emission, astronomers can trace the distribution and motion of cold gas throughout our galaxy, revealing the complex dynamics of cloud formation, collapse, and dispersal. Perhaps the most remarkable aspect of the cold interstellar medium is its role as both ending and beginning. It represents the dispersed remains of previous generations of stars, their outer layers expelled through stellar winds or supernova explosions, now cooled to these frigid temperatures. Yet it also contains the seeds of future stellar generations, the condensing cores that will eventually ignite to form new stars and planetary systems. In this way, the cold between stars connects the past and future of our galaxy in a continuous cycle of stellar birth, life, and death. As travelers moving through space, we would perceive the interstellar medium primarily by its absence, the near vacuum that separates the islands of warmth we call stars. Yet this apparent emptiness, cold and dark though it may be, contains the diffuse material from which all stars, planets, and ultimately living things are formed. The cold of interstellar space is not a void but a reservoir, storing the elements of past stars until gravity cools them together once more. Paradoxically, in these icy nurseries, stars begin to stir. Having explored the general nature of the cold interstellar medium, we now focus our attention on its most fascinating manifestations, the giant molecular clouds. These enormous structures represent the coldest substantial regions in our galaxy, cosmic refrigerators where temperatures hover around 10 Kelvin, or negative 263 degrees Celsius. Within these frigid realms, chemistry and physics operate under conditions so extreme that they create phenomena impossible to replicate naturally on Earth. Molecular clouds earn their name from their primary constituent, molecules rather than individual atoms. While this might seem unremarkable from our Earth perspective, where nearly everything consists of molecules in the context of the universe, molecular matter is relatively rare. Most of the ordinary matter in the cosmos exists either as plasma, the superheated state where electrons separate from nuclei, or as neutral atoms, The formation of stable molecules requires specific conditions, particularly the shelter from energetic radiation that would otherwise break molecular bonds. The cold, dense environments of molecular clouds provide exactly this protection. The largest of these structures, the giant molecular clouds, rank among the most massive objects in our galaxy. A typical giant molecular cloud contains between 100,000 and several million times the mass of our Sun, concentrated in regions spanning tens to hundreds of light years. Despite this enormous mass, molecular clouds remain nearly invisible to optical telescopes. Their presence was unknown until the mid-20th century, when radio astronomy revealed the distinctive emission lines of carbon monoxide and other molecules that trace these hidden structures. The Milky Way contains thousands of molecular clouds, with the largest congregating along the spiral arms where gas naturally concentrates. Famous examples include the Orion molecular cloud, associated with the visible Orion Nebula, and the Taurus molecular cloud, a nearby star-forming region that has been extensively studied. These vast cold reservoirs contain enough material to form thousands or even millions of stars, making them the primary nurseries for new stellar systems in our galaxy. What makes molecular clouds truly remarkable is their temperature. At around 10 Kelvin, they are among the coldest naturally occurring substantial objects in the universe, exceeded in their chill only by specialized structures like the Boomerang Nebula that we explored earlier. This profound cold results from their excellent insulation from external heating sources, combined with efficient cooling mechanisms that radiate away thermal energy. The insulation of molecular clouds comes primarily from dust, those microscopic solid particles that make up about 1% of the interstellar medium by mass. These dust grains, typically less than a micrometer in size, are remarkably effective at absorbing and scattering ultraviolet and visible light, the wavelengths that carry most of the heating energy from nearby stars. The outer layers of dust in a molecular cloud act as a shield, preventing this energetic radiation from penetrating to the interior and warming the gas there. Cooling within molecular clouds occurs through a process known as radiative cooling. Molecules like carbon monoxide, water, and other trace species can become excited through collisions with hydrogen molecules, the most abundant constituent of the cloud. These excited molecules then emit photons in the infrared and radio portions of the spectrum, wavelengths that can easily escape the cloud due to its relative transparency at these longer wavelengths. This process effectively converts kinetic energy, the random motion of molecules that we measure as temperature, into radiation that leaves the cloud, progressively cooling the gas. The balance between the minimal heating that penetrates into the cloud and this efficient cooling mechanism establishes the characteristic temperature of around 10 Kelvin found in the densest regions. This temperature is not uniform throughout the cloud, but varies with density and distance from the cloud's edge. The outer layers, more exposed to external radiation, may reach 20 to 30 Kelvin, while the most shielded interior regions can drop to as low as 7 Kelvin. At these extreme temperatures, most of the chemical species that would be gases on Earth freeze onto the surfaces of dust grains. Water, carbon dioxide, ammonia, methane, and many other volatile compounds exist primarily as ices rather than gases in the depths of molecular clouds. Only hydrogen and helium, along with some trace molecules like carbon monoxide, remain substantially in the gas phase. This freezing out process dramatically changes the chemistry that can occur, limiting certain reaction pathways while enabling others that would be impossible in warmer environments. The ice mantles that form on dust grains in these cold regions create a distinct chemistry of their own. As atoms and molecules from the gas phase collide with and stick to these icy surfaces, they can migrate across the surface and react with other adsorbed species. The dust grain itself acts as a catalyst, bringing reactive species together and, in some cases, lowering the energy barriers that would otherwise prevent reactions. This surface chemistry produces complex molecules that cannot form efficiently in the gas phase, including some organic compounds of astrobiological interest. The extreme cold also affects the physical state of these ice mantles. Rather than forming the crystalline structures we associate with ice on Earth, the ices in molecular clouds typically exist in an amorphous state, a disordered arrangement more akin to glass than to crystalline solids. This amorphous ice can trap other molecules within its structure, creating a complex mixture that records the chemical history of the dust grain's journey through the cloud. One of the most remarkable consequences of the cold in molecular clouds is its effect on the chemistry of hydrogen, the most abundant element in the universe. Molecular hydrogen, H2, can exist in two forms based on the alignment of the nuclear spins of its constituent atoms. These forms, known as orthohydrogen and parahydrogen, have slightly different energy levels. At room temperature, the ratio of ortho to parahydrogen is fixed at 3:1. But at the extreme cold of molecular clouds, the lower energy para form is thermodynamically favored. However, the conversion from ortho to parahydrogen proceeds extremely slowly in the diffuse environment of space. This creates a situation where the measured ratio of these two forms can reveal the thermal history of the gas. Gas that has been cold for a very long time will show a higher proportion of the para form, while gas that has been recently cooled may retain a ratio closer to the warm equilibrium value. Astronomers use these measurements as a kind of cosmic thermometer, tracing the temperature history of molecular gas. The cold temperatures within molecular clouds also promote quantum mechanical effects that would be obscured by thermal motion in warmer environments. Quantum tunneling, where particles can pass through energy barriers that classical physics would deem insurmountable, becomes increasingly important in driving chemical reactions. This allows certain reactions to proceed even at temperatures so low that the reactants would not have enough thermal energy to overcome the activation energy barrier. Giant molecular clouds are not homogeneous structures but contain intricate substructures shaped by gravity, turbulence, and magnetic fields. High-resolution observations reveal a hierarchical organization, with the cloud fragmented into clumps, which themselves contain denser cores where star formation may be beginning. This structure reflects the interplay between the cloud's self-gravity, which works to collapse the material, and various forms of pressure and magnetism that resist this collapse. The densest cores within molecular clouds, known as prestellar cores, represent the sites where star formation is imminent or already underway. These cores, typically less than a light year across, have central densities thousands of times greater than the surrounding cloud, and sometimes contain young stars or protostars hidden from view at visible wavelengths. Despite beginning to warm in their very centers due to gravitational compression, the outer regions of these cores remain extremely cold, often showing temperatures as low as 7 to 8 Kelvin. As star formation progresses within these cores, the emerging protostar begins to heat its surroundings, creating a temperature gradient that drives complex chemistry. Different molecular species form, freeze out, or sublimate at different distances from the warming center, creating a layered chemical structure that astronomers can observe with radio telescopes. This chemical differentiation provides valuable information about the age and evolutionary stage of the forming stellar system. The cold gas in molecular clouds does not remain stationary, but moves in complex patterns driven by turbulence, rotation, gravitational collapse, and outflows from young stars. These motions create the characteristic filamentary structures observed in high-resolution images of molecular clouds, with dense gas appearing to flow along these filaments toward the densest cores. The velocities involved are typically just a few kilometers per second, slow by astronomical standards, but still supersonic, given the extreme cold of the gas. These supersonic motions create shock waves that compress the gas and momentarily heat small regions before they quickly radiate away this excess energy. These shocks can trigger chemical reactions that would not occur in the undisturbed gas, producing transient species that serve as markers of these dynamic processes. The shocks also contribute to the overall turbulence of the cloud, a key factor in regulating the rate and efficiency of star formation. While the interior of molecular clouds remains hidden from optical telescopes, modern infrared and radio observatories have revealed their structure in extraordinary detail. The Herschel Space Observatory, specifically designed to observe cool cosmic dust, mapped the filamentary structure of nearby molecular clouds with unprecedented clarity. The Atacama Large Millimeter Array, with its ability to detect the emission from various molecular species, has revealed the chemical complexity of these cold environments. And the James Webb Space Telescope, with its unparalleled infrared sensitivity, can penetrate the dusty veil to observe the young stars forming within. These observations reveal that star formation within molecular clouds is not an isolated process, but occurs in clustered environments with multiple stars forming from the same cloud complex. The most massive molecular clouds can give rise to hundreds or thousands of stars over millions of years, creating stellar associations and clusters that share a common origin. The feedback from the first stars to form, through their radiation and stellar winds, can both trigger the formation of additional stars and eventually disperse the remaining cold gas, terminating the star formation process. The cold of molecular clouds serves not just as a facilitator of star formation, but also as a preserver of information about the chemical and physical history of our galaxy. The molecules formed and maintained in these frigid environments carry isotopic signatures that reflect the nucleosynthetic processes in previous generations of stars. By measuring the ratios of different isotopes in molecules like carbon monoxide or ammonia, astronomers can trace the enrichment of the interstellar medium by stellar winds and supernova explosions over the lifetime of the galaxy. One of the most intriguing aspects of the cold molecular gas in our galaxy is its role in potentially harboring the building blocks of life. The molecular inventory of cold clouds includes many organic compounds, some quite complex. Astronomers have detected amino acids, the building blocks of proteins, as well as sugars and other biologically relevant molecules in these environments. The cold preserves these delicate compounds, which would quickly dissociate at higher temperatures, allowing them to accumulate over millions of years. This connection to potential biological precursors has led some scientists to propose that molecular clouds may play a role in the origin of life on planets like Earth. As these clouds give birth to new stars and planetary systems, some of their complex organic inventory can be incorporated into comets and asteroids that later deliver this material to forming planets. In this way, the extreme cold of molecular clouds may have contributed to the chemical inventory that eventually led to life on our own planet. The temperature structure within molecular clouds also affects the initial mass distribution of the stars that form there. The coldest, densest regions tend to fragment into relatively small cores, leading to the formation of low-mass stars like our Sun or smaller. In contrast, regions that are warmer or more turbulent may form fewer, more massive cores that can grow into high-mass stars. This temperature-dependent fragmentation process helps shape the overall distribution of stellar masses in our galaxy. The magnetic fields that permeate molecular clouds play a crucial role in their evolution and in regulating their temperature. These fields provide additional support against gravitational collapse, slowing the contraction of the gas and allowing it to cool more effectively. The fields also channel the flow of ionized gas and cosmic rays, affecting both the heating rate and the ability of the cloud to dissipate angular momentum during collapse, a necessary step in the formation of stars and planetary systems. Observations of polarized light from background stars shining through molecular clouds allow astronomers to map these magnetic fields. The elongated dust grains within the cloud tend to align their long axes perpendicular to the magnetic field lines, creating a slight polarization in the light that passes through. These polarization maps reveal the overall structure of the magnetic field and its relationship to the dense filaments and cores where stars are forming. The coldest molecular clouds are not distributed evenly throughout our galaxy, but concentrate primarily in the spiral arms, where gas naturally gathers due to the galaxy's differential rotation. This concentration creates a pattern of star formation that follows the spiral structure, with new stars predominantly forming along these arms. The movement of clouds through the spiral arms also subjects them to compression, which can trigger or accelerate star formation, creating a wave of stellar birth that propagates through the galaxy. Beyond our own galaxy, molecular clouds serve as the primary sites of star formation in other galaxies as well. Observations of nearby galaxies reveal that their star formation rates correlate strongly with the amount of cold molecular gas they contain. Galaxies rich in cold gas, like many spiral and irregular galaxies, show active star formation, while galaxies depleted of cold gas, like most elliptical galaxies, have largely ceased forming new stars. This universal connection between cold molecular gas and star formation underscores the fundamental importance of these frigid environments in cosmic evolution. The study of molecular clouds in other galaxies is challenging due to their distance, but has been revolutionized by modern millimeter wave interferometers like ALMA. These observations reveal that the basic properties of giant molecular clouds appear similar across different galaxies, suggesting that the physical processes governing their formation and evolution are universal. However, differences in metallicity, radiation field, and galactic structure can affect the detailed temperature and chemistry of these extragalactic clouds. The future of molecular clouds in our own galaxy is intimately tied to the ongoing processes of star formation and feedback. As stars form within these cold reservoirs, their radiation and winds gradually erode and warm the surrounding gas. Eventually, supernova explosions from the most massive stars can disperse the cloud entirely, recycling its material back into the more diffuse interstellar medium. This dispersed material will eventually cool and condense again to form new molecular clouds, continuing the cycle of stellar birth and death. As we contemplate these vast cold structures, it is worth reflecting on their dual nature. Despite their frigid temperatures, molecular clouds are sites of creation and renewal, the birthplaces of new stars and planetary systems. Their cold does not represent stagnation, but rather a necessary condition for the gravitational processes that lead to stellar birth. In these environments, cold is not the absence of activity, but rather a prerequisite for some of the most fundamental processes in galactic evolution. The study of cold molecular gas connects some of the largest scales in astronomy with some of the smallest. From the galactic scale distribution of molecular clouds to the quantum mechanical effects that drive their chemistry at the atomic level, understanding these frigid environments requires bridging vast differences in scale. It is a testament to modern astronomy that we can now observe both the overall structure of these clouds across light years and the detailed chemical processes occurring on the surfaces of microscopic dust grains. The cold does not destroy here, it preserves, it prepares, it waits. Our journey through the coldest places in the universe now takes a remarkable turn. Having explored the natural cold of cosmic voids, the Boomerang Nebula, and the frigid molecular clouds scattered throughout our galaxy, we now encounter cold of a different origin. Here, on our warm planet Earth, orbiting an average star in the suburbs of the Milky Way, an ingenious species has created temperatures colder than anywhere else in the known universe. Human beings, through intellectual curiosity and technological innovation, have engineered environments that plunge to within billionths of a degree above absolute zero, colder than the deepest reaches of space. This achievement represents one of humanity's most impressive scientific accomplishments. Through a series of discoveries and innovations spanning more than a century, scientists have progressively approached the ultimate cold of absolute zero, that theoretical temperature where all thermal motion would cease. While the laws of thermodynamics tell us that absolute zero can never be fully reached, the temperatures achieved in modern laboratories come astonishingly close, allowing us to observe phenomena that exist nowhere else in the cosmos. The quest for extreme cold began in the 19th century, when scientists first liquefied the so-called permanent gases, those that remain gaseous at normal atmospheric pressure and temperature. Michael Faraday successfully liquefied chlorine in 1823, but nitrogen, oxygen, and hydrogen proved more challenging. By 1877, Louis-Paul Cailletet and Raoul Pictet had independently liquefied oxygen, reaching temperatures of around 90 Kelvin or negative 183 degrees Celsius. The race to ever lower temperatures continued with James Dewar, who liquefied hydrogen in 1898, reaching a temperature of about 20 Kelvin. This achievement allowed him to construct the first vacuum flask, now known as the Dewar flask or thermos, to store these cryogenic liquids. The final naturally occurring gas to be liquefied was helium, accomplished by Heike Kamerlingh-Onnes in 1908, reaching a temperature of about 4.2 Kelvin or negative 269 degrees Celsius. These early achievements in creating cold relied primarily on a principle known as the Joule-Thomson effect, where a gas cools as it expands. By compressing a gas, allowing it to cool, and then permitting it to expand rapidly, scientists could progressively lower its temperature until it liquefied. Once one gas was liquefied, it could be used as a coolant to help liquefy gases with even lower boiling points, creating a cascade of ever-decreasing temperatures. A major milestone came in 1911 when Kamerlingh-Onnes discovered superconductivity, the complete disappearance of electrical resistance in certain materials when cooled below a critical temperature. This discovery, made while studying Mercury at liquid helium temperatures, opened a new chapter in low-temperature physics and demonstrated that truly novel phenomena emerge in the extreme cold. Onnes received the Nobel Prize in Physics in 1913 for his groundbreaking work on the properties of matter at low temperatures. Pushing to even colder temperatures required new approaches. In the 1920s and 1930s, scientists developed magnetic cooling techniques, where certain paramagnetic salts are cooled by aligning their magnetic moments in a strong magnetic field and then removing the field, causing the temperature to drop further. This method allowed William Francis Joke to reach temperatures below 1 Kelvin, earning him the 1949 Nobel Prize in Chemistry. Another significant advance came with the development of the helium-3 refrigerator. Helium-3, the lighter isotope of helium with 2 protons and 1 neutron, remains liquid at lower temperatures than the more common helium-4. By 1950, temperatures as low as 0.7 Kelvin had been achieved using liquid helium-3. The combination of helium-3 and helium-4 led to one of the most powerful cooling techniques, the dilution refrigerator. This device, developed in the 1960s, exploits the quantum properties of these two isotopes when mixed at very low temperatures. When helium-3 dissolves into helium-4, it absorbs heat, producing cooling. By continuously circulating helium-3 through a bath of helium-4, scientists can maintain temperatures as low as about 2 millikelvin or 0.002 of a degree above absolute zero. But the most dramatic advance in the creation of extreme cold came with the development of laser cooling techniques in the 1980s. Rather than cooling bulk materials, this approach targets individual atoms, using precisely tuned lasers to slow their motion. While it might seem counterintuitive that light can cool matter, the process works because the laser is tuned slightly below the resonant frequency of the target atoms. Due to the Doppler effect, atoms moving toward the laser see its frequency shifted upward, bringing it into resonance and causing them to absorb photons and slow down. The technique is sometimes described as optical molasses, as the atoms move as if through a thick, resistive medium. By combining laser cooling with other techniques like evaporative cooling, where the warmest atoms are allowed to escape, leaving behind a colder sample, physicists have created the coldest matter in the universe. In 1995, a team led by Eric Cornell and Carl Wyman at the University of Colorado created the first Bose-Einstein condensate, a new state of matter predicted by Albert Einstein and Satyendra Nath Bose 70 years earlier. This achievement, which earned them the 2001 Nobel Prize in Physics along with Wolfgang Ketterle, involved cooling a gas of rubidium atoms to about 170 nanokelvin, or 170 billionths of a degree above absolute zero. Since then, even lower temperatures have been achieved. In 2003, researchers at MIT cooled a sodium gas to about 500 picokelvin, or 500 trillionths of a degree above absolute zero. More recently, in 2017, a team at the National Institute of Standards and Technology achieved a record low temperature of about 100 picokelvin in a gas of potassium atoms. These temperatures are so extraordinarily cold that they defy everyday intuition. They are billions of times colder than interstellar space, and trillions of times colder than the average temperature on Earth. What makes these achievements particularly remarkable is that they occur on our warm planet, where the ambient temperature is typically around 300 Kelvin. Creating and maintaining these ultra-cold environments requires extraordinary insulation and precision engineering to prevent the heat of the surroundings from flooding in. It is as if we have created tiny islands of extreme cold in an ocean of warmth, isolated bubbles of quantum strangeness in our otherwise classical world. The technologies developed to create these extreme temperatures have applications far beyond the laboratory. Superconducting magnets, which operate at liquid helium temperatures, are essential components of MRI machines used in medical diagnostics and of particle accelerators used in fundamental physics research. Infrared sensors cooled to cryogenic temperatures provide enhanced sensitivity for astronomy and defense applications, and the precise atomic clocks that enable global positioning systems rely on laser cooling techniques similar to those used to create the coldest temperatures. One particularly fascinating application of human-created cold is the Cold Atom Lab, a facility installed on the International Space Station in 2018. This unique laboratory creates Bose-Einstein condensates in the microgravity environment of orbit, allowing them to be observed for much longer periods than is possible on Earth, where gravity causes these delicate quantum systems to quickly fall and disperse. The Cold Atom Lab represents the lowest naturally occurring temperatures in our solar system, a remarkable achievement of human engineering. In these artificially created cold environments, matter behaves in ways that seem almost magical compared to our everyday experience. Quantum effects, normally hidden by the thermal jiggling of atoms, become dominant and directly observable. Perhaps the most striking example is superfluidity, a state where fluids flow with absolutely no viscosity or friction. Liquid helium-4, when cooled below about 2.17 Kelvin, becomes a superfluid that can flow uphill through seemingly solid barriers and remain in perpetual motion. Even more exotic is the behavior of Bose-Einstein condensates, where thousands or millions of atoms lose their individual identities and behave as a single coherent quantum entity. These condensates can display wave-like properties normally associated with subatomic particles, creating interference patterns similar to those produced by light waves. They can also form quantized vortices, tiny whirlpools where the rotation occurs in discrete steps rather than continuously. Another manifestation of quantum mechanics at the macroscopic scale. The study of ultra-cold matter has led to the development of quantum simulators, specialized devices that use cold atoms arranged in optical lattices created by intersecting laser beams to model complex quantum systems that would be impossible to simulate with conventional computers. These simulators allow scientists to investigate phenomena like high-temperature superconductivity and quantum magnetism, potentially leading to new materials with revolutionary properties. Another application of extreme cold is in quantum computing, where information is stored and processed using quantum states rather than classical bits. Many quantum computing approaches require extremely low temperatures to maintain quantum coherence, the delicate quantum state that allows for the unique capabilities of these computers. The most advanced quantum computers today operate at temperatures around 15 millikelvin, using dilution refrigerators to create and maintain this extreme cold. The creation of such extreme cold represents a triumph of human ingenuity and persistence. Each step toward absolute zero has required overcoming significant technological challenges and has often revealed unexpected physical phenomena. The quest has been driven not primarily by practical applications, though these have emerged, but by the fundamental human desire to explore the unknown, to push the boundaries of what is possible, and to understand the basic laws that govern our universe. The extreme cold created in laboratories allows scientists to test the laws of physics in regimes never before accessible. Quantum theories that make predictions about the behavior of matter at absolute zero can be tested with unprecedented precision. General relativity and quantum mechanics, our two most successful but seemingly incompatible physical theories, can be probed in new ways, potentially shedding light on how they might be reconciled in a theory of quantum gravity. One particularly active area of research involves using ultra-cold atoms to study quantum many-body physics, the complex behavior that emerges when large numbers of quantum particles interact. These systems can display phenomena like quantum phase transitions, where the system undergoes a fundamental change in its properties, not due to temperature changes, as in conventional phase transitions, but due to quantum fluctuations at absolute zero. Understanding these exotic states of matter could lead to new technologies in computing, communication, and energy. The human-created cold also allows for precise measurements that would be impossible under normal conditions. The first atomic clocks, developed in the 1950s, were accurate to about 1 second in 3,000 years. Modern atomic clocks, using laser-cooled atoms, are accurate to about 1 second in 15 billion years, longer than the age of the universe. This extraordinary precision enables not just practical applications like GPS, but also fundamental physics tests, such as searching for variations in the constants of nature or testing Einstein's theory of relativity. As impressive as these achievements are, the quest for ever lower temperatures continues. New cooling techniques, combining the best aspects of existing methods with novel approaches, promise to push even closer to absolute zero. One such technique is nuclear demagnetization, which uses the magnetic properties of atomic nuclei rather than electrons to achieve cooling. While extraordinarily difficult to implement, this method has the potential to reach temperatures in the picokelvin range for macroscopic samples, not just for dilute gases. Another frontier involves creating cold molecules rather than just cold atoms. Molecules, with their additional rotational and vibrational degrees of freedom, present unique challenges for cooling, but also offer new opportunities for quantum control and information processing. Recent years have seen significant progress in creating ultra-cold molecules, either by cooling them directly or by forming them from already cold atoms. The extreme cold engineered by humans also provides a unique perspective on the cold of outer space. While the average temperature of interstellar space, at around 2.7 Kelvin, seems incredibly cold by everyday standards, it is positively toasty compared to the nanokelvin temperatures achieved in laboratories. This comparison highlights the remarkable fact that some of the most extreme conditions in the entire universe exist not in exotic astronomical objects, but in small, carefully controlled environments created by human intelligence. This achievement represents a kind of inversion of our usual relationship with cosmic extremes. We cannot create the crushing densities found in neutron stars or the searing temperatures of stellar cores, but we have surpassed the universe in creating cold. It is as if, in this one dimension of physical extremity, humanity has exceeded the natural limits of the cosmos, crafting conditions more extreme than nature itself provides. The philosophical implications of this achievement are profound. In creating temperatures colder than anywhere in the natural universe, humans have demonstrated a capacity to transcend, in at least this limited way, the conditions of the cosmos that gave rise to us. We have not merely adapted to our environment or shaped it to our needs, as all life does to some extent, but have fundamentally transformed it, creating conditions that have never before existed in the history of the universe. This capacity for transformation reflects something essential about human nature. Unlike other species, which evolved to fit their environments, humans increasingly shape environments to fit our evolving knowledge and aspirations. The creation of extreme cold exemplifies this distinctively human approach to existence, where curiosity and creativity lead us to reshape reality itself in our quest for understanding. Yet even as we celebrate this remarkable achievement, we should remember that our mastery of cold remains limited and fragile. The ultra-cold environments created in laboratories exist only in tiny volumes and for brief periods, sustained by complex machinery that itself depends on the warmer world around it. Our islands of extreme cold remain surrounded by the ocean of warmth that makes human life possible. This dependence reminds us that for all our technological prowess, we remain part of the natural world, not separate from it. The same laws of physics that we explore in our coldest laboratories govern the stars that warm our planet and the biological processes that sustain our lives. Our ability to create extreme cold does not exempt us from these laws, but rather demonstrates our growing understanding of them and ability to work within their constraints to achieve our goals. As we look to the future, the human mastery of cold promises new discoveries and technologies that may transform our understanding of the universe and our place within it. Quantum computers operating at ultra-low temperatures may solve problems beyond the reach of classical computation. New states of matter, existing only near absolute zero, may display properties that revolutionize materials science and engineering, and increasingly precise measurements may reveal subtle effects that lead to breakthroughs in fundamental physics. The cold engineered by humans is more than just a scientific achievement. It is a testament to our unique capacity to understand and reshape our world, to push beyond the limits that nature has set, and to create conditions for discovery that the universe itself does not provide. In these coldest places of human creation, we glimpse not just the strange behavior of matter at the quantum scale, but also something profound about ourselves and our relationship to the cosmos. We chase the cold not just to endure it, but to understand the universe itself. Having explored how humans have created temperatures colder than anywhere in the natural universe, we now venture deeper into the strange and fascinating physics that emerges in these extreme conditions. As matter approaches absolute zero, the lowest possible temperature where all thermal motion would theoretically cease, it begins to behave in ways that defy our everyday intuition. The familiar rules that govern our warm world fade away, replaced by the subtle and often counterintuitive principles of quantum mechanics. Absolute zero, defined as 0 Kelvin or negative 273.15 degrees Celsius, represents a theoretical limit that can never be fully reached according to the third law of thermodynamics. As scientists push ever closer to this ultimate cold, approaching within billionths or even trillionths of a degree, they enter a realm where the very nature of matter transforms. Here, in this quantum playground, particles cease to behave as distinct entities with definite positions and instead spread out into probability waves that can overlap and interfere. To understand the physics of near absolute zero, we must first appreciate how fundamentally temperature relates to motion. What we perceive and measure as temperature is, at the microscopic level, simply the random motion of atoms and molecules. In a gas at room temperature, particles zip about at hundreds of meters per second, constantly colliding and changing direction. As temperature decreases, this motion slows. By the time we reach the frigid environments of laboratory cold traps, with temperatures in the nanokelvin range, atoms move at mere millimeters per second or slower. But quantum mechanics tells us that this slowing cannot continue indefinitely. According to Heisenberg's uncertainty principle, it is impossible to know both the position and momentum of a particle with perfect precision. As temperature approaches absolute zero and thermal motion diminishes, the uncertainty in a particle's position grows. The particle, rather than settling into a perfectly defined location, becomes delocalized, existing as a probability wave spread over a measurable distance. This quantum delocalization leads to one of the most remarkable states of matter ever discovered, the Bose-Einstein condensate. Predicted by Albert Einstein and Satyendra Nath Bose in the 1920s, but not created in a laboratory until 1995, a Bose-Einstein condensate forms when a gas of bosons, particles with integer spin like helium-4 atoms or rubidium atoms, is cooled to near absolute zero. At these extreme temperatures, the quantum wavelengths associated with individual atoms begin to overlap. Once the temperature drops low enough, a dramatic transition occurs. The atoms, which previously behaved as separate particles, suddenly coalesce into a single quantum state. Thousands or even millions of atoms begin to behave as one coherent entity, a macroscopic quantum object that follows the laws of wave mechanics rather than classical particle physics. This transformation is not gradual, but occurs abruptly at a specific critical temperature. Above this temperature, the gas behaves more or less normally. Below it, a significant fraction of the atoms occupies the lowest energy state, forming what physicists call a condensate fraction. As the temperature decreases further toward absolute zero, more and more atoms join this condensate until, theoretically, all would participate in the collective quantum state at absolute zero itself. The creation of Bose-Einstein condensates in the laboratory has allowed scientists to observe quantum behavior on a macroscopic scale. These condensates exhibit wave-like properties that can be directly visualized. When two separate condensates are allowed to expand and overlap, they create interference patterns similar to those produced when light waves intersect, providing direct evidence of their wave nature. Perhaps even more striking is the phenomenon of superfluidity, a state where fluids flow with absolutely no viscosity or resistance. Helium-4, when cooled below 2.17 Kelvin, becomes a superfluid that can perform feats impossible for ordinary liquids. It can flow through nanoscale pores that would block normal fluids, climb up and over the walls of its container, and remain in perpetual motion, its flow never diminishing due to friction. This Superfluidity arises directly from quantum mechanics and the formation of a Bose-Einstein condensate within the liquid. The helium atoms in the condensate fraction move as a coordinated whole, making it impossible for individual atoms to scatter and create the dissipation we experience as viscosity. The result is perfect, frictionless flow, one of the most dramatic manifestations of quantum behavior on a scale visible to the naked eye. Fermions, particles with half-integer spin like electrons and certain atomic isotopes, cannot form Bose-Einstein condensates due to the Pauli exclusion principle, which forbids them from occupying the same quantum state. However, at sufficiently low temperatures, fermions can pair up to form composite bosons, which can then condense. This mechanism underlies both superconductivity, the flow of electricity without resistance, and superfluidity in helium-3, which becomes a superfluid at much lower temperatures than helium-4. The physics of these paired fermion systems is extraordinarily rich and complex. In conventional superconductors, electrons form Kuiper pairs due to vibrations in the crystal lattice, creating a state that allows current to flow without resistance. In helium-3 superfluid, the atoms themselves pair up through magnetic interactions, forming a condensate with internal structure that can exist in multiple distinct phases depending on temperature, pressure, and magnetic field. Another fascinating phenomenon that emerges at ultra-low temperatures is the quantization of physical properties that appear continuous in our everyday experience. Vortices in superfluid helium, for instance, can only have certain discrete values of circulation, rather than the continuous range possible in classical fluids. Similarly, the conductance of quantum point contacts, tiny constrictions in electronic circuits cooled to near absolute zero, is quantized in units of a fundamental constant, regardless of the specific material or geometry. This quantization reflects a fundamental aspect of quantum mechanics, the discreteness of nature at its most basic level. Properties that seem continuous in our warm, macroscopic world reveal their quantized nature as thermal fluctuations diminish near absolute zero. What we perceive as smooth, continuous variation is often a statistical average over many discrete quantum events, an illusion dispelled in the clarifying cold of quantum environments. The approach to absolute zero also reveals the quantum ground state of matter, the lowest energy configuration allowed by quantum mechanics. Unlike the classical ground state, where particles would simply stop moving at absolute zero, the quantum ground state contains irreducible motion known as zero-point energy. This energy, present even at absolute zero due to Heisenberg's uncertainty principle, ensures that matter remains dynamic even in the complete absence of thermal excitation. The structure of this quantum ground state can be extraordinarily complex and information-rich. In certain materials, particularly those with strong electron correlations, the ground state may exhibit exotic properties like topological order, where the system remembers its history through global rather than local features. These topological states are of great interest for quantum computing, as they may allow for the storage and processing of quantum information in ways resistant to local disturbances. As temperatures drop towards absolute zero, the thermal energy available to overcome energy barriers diminishes, making certain processes extremely slow or virtually non-existent. However, quantum tunneling, the ability of particles to pass through energy barriers rather than over them, becomes increasingly significant. This tunneling process, which has no classical analog, allows for chemical reactions and physical transitions that would be impossible according to classical physics. In some cases, this quantum tunneling can lead to surprising dynamic behavior, even at temperatures very close to absolute zero. Certain molecular rotors, for instance, continue to rotate through quantum tunneling even when thermal energy is insufficient to overcome the barriers to rotation. Similarly, protons in some hydrogen-bonded systems can tunnel between different positions, creating quantum superpositions that affect the material's properties. The dominance of quantum effects near absolute zero extends to the magnetic properties of materials as well. In conventional magnets, the alignment of electron spins produces a magnetic field. As temperature decreases, thermal disruption of this alignment diminishes, and the magnetization increases. However, in certain materials known as quantum magnets, quantum fluctuations prevent the spins from aligning even at absolute zero, creating states known as quantum spin liquids, where the magnetic moments remain disordered and dynamic. These quantum spin liquids represent another example of how the approach to absolute zero can reveal states of matter with no classical analog. Rather than freezing into static configurations as classical intuition might suggest, these systems maintain quantum fluctuations that prevent any single configuration from dominating. The result is a kind of quantum superposition of many different spin arrangements, a complex entangled state that challenges our ability to visualize or describe in classical terms. The study of matter near absolute zero has also led to the discovery of quantum phase transitions, fundamentally different from the classical phase transitions we observe in everyday life. Classical phase transitions, like water freezing to ice, are driven by thermal fluctuations and occur at non-zero temperatures. Quantum phase transitions, in contrast, occur at absolute zero and are driven by quantum fluctuations as some non-thermal parameter, like pressure or magnetic field, is varied. These quantum phase transitions often exhibit universal behavior, independent of the specific details of the system, reflecting fundamental organizing principles in quantum many-body physics. They can influence material properties even at temperatures well above absolute zero, creating what physicists call quantum critical regions, where neither fully quantum nor fully classical descriptions suffice. Some of the most enigmatic materials in condensed matter physics, including certain high-temperature superconductors, may owe their unusual properties to proximity to quantum critical points. The extreme cold near absolute zero also allows for the creation of quantum gases with precisely controlled interactions. By applying magnetic fields to ultra-cold atomic gases, experimentalists can tune the strength and even the sign of interactions between atoms, creating systems that range from strongly attractive to strongly repulsive, with a special condition known as a Feshbach resonance, where the interaction strength diverges. This ability to dial in different interaction regimes has allowed scientists to explore the crossover between Bose-Einstein condensation, where bosonic atoms directly form a collective quantum state, and Bardeen-Cooper-Schrieffer superfluidity, where fermionic atoms first pair up and then condense. This research has provided insights into strongly correlated quantum systems that could not be obtained through any other experimental approach. Another remarkable phenomenon observed near absolute zero is the reduced speed of light in certain media. When light passes through a Bose-Einstein condensate, it can be slowed to just a few meters per second, less than 100 millionth of its speed in vacuum. In some experiments, light has even been brought to a complete stop, stored as an excitation within the condensate, and then released to continue its journey. This ability to manipulate the most fundamental constant of nature, the speed of light, demonstrates the extraordinary control over physical processes that becomes possible in the quantum realm. The physics of ultra-low temperatures extends beyond condensed matter to fundamental questions in quantum information theory. Quantum entanglement, the spooky action at a distance that troubled Einstein, can be studied with unprecedented clarity and control in systems cooled near absolute zero. These experiments have confirmed the non-local nature of quantum mechanics and laid the groundwork for emerging technologies like quantum cryptography and quantum computing. Quantum computers, which process information using quantum bits or qubits that can exist in superpositions of states, often require extremely low temperatures to function. The superconducting qubit architecture, one of the leading approaches to quantum computing, typically operates at temperatures around 15 millikelvin. At these temperatures, thermal noise is sufficiently suppressed to allow quantum coherence to persist long enough for meaningful computations to be performed. The relationship between temperature and quantum coherence highlights a fundamental aspect of the approach to absolute zero. As thermal fluctuations diminish, quantum correlations and entanglement can extend over larger distances and longer times. In a sense, the coldest environments are those where the quantum nature of reality becomes most evident, where the veil between the classical world of our everyday experience and the quantum substrate beneath it grows thinnest. This connection between cold and quantum behavior extends even to our understanding of the early universe. In the first moments after the Big Bang, despite the extreme heat, certain quantum fields underwent transitions analogous to the condensation of ultra-cold atomic gases. The cosmic microwave background radiation, which we now observe at a frigid 2.7 Kelvin, contains subtle patterns that may reflect quantum fluctuations from the earliest epochs of cosmic history. expanded to astronomical scales by the subsequent inflation of the universe. The physics of near absolute zero also provides insights into the thermodynamics of information, a field that connects the abstract concept of information with physical reality. As demonstrated by experiments on Maxwell's demon and Landauer's principle, information has physical consequences, and its manipulation requires energy. At temperatures approaching absolute zero, where thermal energy becomes vanishingly small, these connections between information and thermodynamics become particularly significant. Some of the most challenging questions in this field involve the thermodynamics of quantum information. How does quantum entanglement relate to thermodynamic entropy? Can quantum resources allow for more efficient use of energy in computation? What happens to information that falls into a black hole? And how does this connect to the black hole's thermodynamic properties? Research on quantum systems at ultra-cold temperatures provides a practical arena for exploring these profound theoretical questions. Despite the extraordinary progress in approaching absolute zero, significant challenges remain in pushing to ever lower temperatures and maintaining those temperatures for extended periods. As systems cool, they become increasingly sensitive to tiny heat inputs from their surroundings. Background radiation, vibrations, and even the measurement process itself can introduce energy that heats the system. Creating and preserving temperatures in the picokelvin range requires extraordinary isolation and minimal disturbance. This sensitivity to disturbance connects to a fundamental aspect of quantum mechanics, the measurement problem. The act of measuring a quantum system invariably disturbs it, collapsing wave functions and introducing energy. In the context of ultra-low temperature physics, this means that the very act of observing the coldest systems can warm them, creating a practical manifestation of Heisenberg's uncertainty principle and the observer effect in quantum mechanics. This interplay between observation and disturbance has led to the development of quantum non-demolition measurements, techniques that extract limited information from quantum systems without completely disrupting their state. These approaches, refined in ultra-cold atomic physics experiments, have applications ranging from quantum metrology to gravitational wave detection, where the measurement of extremely small signals requires minimizing the disruption caused by the measurement process itself. The approach to absolute zero also reveals the limits of our current physical theories. Quantum field theory and general relativity, the two pillars of modern physics, have not yet been fully reconciled. Some theorists suggest that a complete theory of quantum gravity might resolve certain paradoxes involving black hole thermodynamics and information preservation. Experiments at ultra-cold temperatures, while not directly probing these high-energy physics questions, provide analogues and insights that inform theoretical work on these fundamental issues. As we look toward future research in ultra-low temperature physics, several exciting frontiers emerge. The creation of more complex quantum gases, including mixtures of different atomic species or molecules with multiple degrees of freedom, promises new states of matter with no natural analogues. The engineering of topological states through precisely controlled interactions could lead to robust quantum memory and computing technologies. And the continued push toward ever lower temperatures may reveal subtle quantum gravitational effects predicted by some theoretical approaches. The practical applications of research near absolute zero extend far beyond the laboratory. Superconducting magnets, operating at liquid helium temperatures, enable magnetic resonance imaging in medicine and provide the intense magnetic fields needed for fusion energy research. Superconducting circuits form the basis for the most sensitive detectors of electromagnetic radiation, used in astronomy and particle physics. And quantum sensors operating at ultra-low temperatures can detect tiny magnetic fields, gravitational variations, and other physical quantities with unprecedented precision. Perhaps the most profound aspect of near absolute zero physics is what it reveals about the nature of reality itself. In our everyday experience, the world appears continuous, deterministic, and governed by classical physics. But as temperatures approach absolute zero and thermal fluctuations diminish, the underlying quantum nature of reality emerges. Matter reveals its wave-like character. Distinctions between particles blur, and the neat categories of classical physics give way to quantum superpositions, entanglement, and complementarity. This transformation reminds us that our intuitive understanding of the world, based on experiences in the warm, macroscopic realm of everyday life, represents only a limited perspective on a deeper reality. The strangeness of quantum mechanics, often discussed as an abstract theoretical construct, becomes concretely manifest in the behavior of matter near absolute zero. The coldest environments created by human ingenuity thus serve as windows into the fundamental nature of the physical world, revealing aspects of reality that would otherwise remain hidden beneath the thermal noise of warmer systems. As we continue our exploration of cold, it is worth reflecting on the remarkable journey that has brought us from the early liquefaction of gases in the 19th century to the creation of temperatures within billionths of a degree of absolute zero today. This progression represents not just a technical achievement, but an expansion of human understanding, a deeper penetration into the subtle architecture of the physical world. The physics of near absolute zero, with its quantum coherence, wave-like matter, and emergent phenomena, offers a glimpse of nature in its most fundamental aspect. Here, in the clarifying cold of temperatures approaching the cosmic limit, the essential character of physical reality reveals itself, not as a collection of distinct objects with definite properties, but as a web of possibilities, probabilities, and interconnections described by the mathematics of quantum theory. As we approach the coldest possible temperature, reality begins to shift. The familiar gives way to the quantum, the intuitive to the mathematical, the separate to the entangled. In this transformation, we find not just exotic states of matter, but a deeper understanding of the universe and our place within it. Through the pursuit of cold, we have uncovered fundamental truths about the nature of physical reality. Truths that might otherwise have remained forever hidden in the thermal noise of our warm world. After exploring the extreme cold engineered in laboratories and the exotic physics that emerges near absolute zero, we now turn our attention to the coldest natural environments closer to home. Our journey takes us first to the frigid regions of our own planet, then outward through our solar system, to discover the diverse cold worlds that orbit our sun. While these environments may not approach the quantum cold of laboratory experiments or the profound chill of interstellar space, they offer fascinating examples of how cold shapes worlds and potentially even the emergence of life. Our planet Earth, despite being at a comfortable distance from the sun, hosts some remarkably cold regions. The lowest natural temperature ever recorded on Earth's surface was measured at Vostok Station in Antarctica, where on July 21, 1983, the temperature plunged to negative 89.2 degrees Celsius. This extreme cold occurred during the perpetual darkness of the Antarctic winter, where sunlight disappears for months and the high elevation of the Antarctic plateau creates conditions for intense radiative cooling. Antarctica as a whole represents Earth's coldest continent, with an average annual temperature of negative 49 degrees Celsius in its interior. The massive ice sheet that covers nearly the entire continent reaches thicknesses of up to 4.8 kilometers, containing about 90% of the world's fresh water in frozen form. This ice has accumulated over millions of years, preserving a record of Earth's climate history in its layers. The extreme cold of Antarctica creates unique ecosystems and specialized life forms. While no indigenous land vertebrates survive in the interior, coastal regions support surprising biodiversity. Emperor penguins have evolved remarkable adaptations to breed during the Antarctic winter, with males incubating eggs in temperatures as low as negative 40 degrees Celsius, while huddling together for warmth. Beneath the sea ice, a rich marine ecosystem thrives, with species like Antarctic krill forming the base of a food web that supports whales, seals, and seabirds. Moving to the northern hemisphere, the Arctic region presents another extremely cold environment, though typically not as severe as Antarctica. The coldest permanently inhabited place on Earth is Oymyakon in the Sakha Republic of Russia, where temperatures have dropped to negative 67.7 degrees Celsius. The roughly 500 residents of this remote village cope with winter temperatures that routinely fall below negative 50 degrees Celsius, in conditions where exhaled breath freezes instantly and mercury thermometers become useless as the metal itself solidifies. The cold of these polar and subpolar regions plays a crucial role in Earth's climate system. The temperature difference between the equator and the poles drives atmospheric circulation, creating the weather patterns that distribute heat and moisture around the globe. The vast ice sheets of Greenland and Antarctica along with the seasonal sea ice of the Arctic Ocean, reflect solar radiation back to space, helping to regulate Earth's temperature through what scientists call the ice albedo feedback. But Earth's surface, even at its coldest, represents a relatively warm environment compared to other places in our solar system. As we leave our home planet and venture outward, we encounter worlds where cold takes on new dimensions. Our nearest celestial neighbor, the Moon, experiences temperature extremes that far exceed anything on Earth due to its lack of a substantial atmosphere. On the lunar surface, temperatures vary dramatically between day and night. During the 2-week lunar day, surface temperatures at the equator can reach 127 degrees Celsius, hot enough to boil water. But during the equally long lunar night, temperatures plummet to negative 173 degrees Celsius. This extreme cold results from the absence of an atmosphere to retain heat, allowing the surface to radiate its warmth directly into space. Even more intriguing are the permanently shadowed craters near the Moon's poles. These deep depressions never receive direct sunlight due to the Moon's slight axial tilt. As a result, temperatures in these areas can drop below negative 230 degrees Celsius, approaching the temperature of liquid nitrogen. These frigid traps have allowed water ice to accumulate over billions of years, creating reservoirs that future lunar explorers might tap for drinking water, rocket fuel, and life support. Moving outward from Earth, we reach Mars, a world that clearly demonstrates the relationship between atmospheric pressure and cold. The thin Martian atmosphere, less than 1% as dense as Earth's, provides little insulation against the cold of space. Surface temperatures on Mars typically range from a relatively mild 20 degrees Celsius during a summer day near the equator to a bitter, negative 125 degrees Celsius at the poles during the winter. Like Earth, Mars experiences seasons due to its axial tilt, but these seasons are more extreme due to the planet's elliptical orbit. The Martian poles host caps of water ice and frozen carbon dioxide, or dry ice, that grow and shrink with the seasons. During the Martian winter, temperatures become cold enough for carbon dioxide to freeze directly from the atmosphere, causing the atmospheric pressure across the entire planet to drop noticeably. The polar regions of Mars reveal some of the strangest landscapes shaped by cold in our solar system. The southern polar cap consists of layers of water ice and dry ice interspersed with dust deposited over millions of years. When spring arrives and sunlight returns, the dry ice sublimates directly from solid to gas, creating distinctive features like spiders. Radial patterns formed as escaping carbon dioxide gas carries dark dust to the surface. Continuing our journey outward, we reach the asteroid belt and encounter a small world with surprising cold features. Ceres, the largest object in the asteroid belt, and now classified as a dwarf planet, was once thought to be an inert, rocky body. However, NASA's Dawn mission revealed bright spots within some of its craters, identified as deposits of salt left behind when water ice sublimated. These findings suggest that despite surface temperatures that can reach negative 38 degrees Celsius at its equator, Ceres contains significant water ice, possibly even a subsurface ocean maintained by radioactive heating in its interior. Beyond the asteroid belt lie the gas giants, beginning with mighty Jupiter. Despite its distance from the Sun, Jupiter actually generates more heat than it receives due to gravitational compression and the slow contraction of its massive bulk. This internal heat source keeps its cloud tops at a relatively mild negative 145 degrees Celsius. However, as we ascend through Jupiter's clouds towards space, temperatures drop dramatically, reaching as low as negative 180 degrees Celsius in the upper atmosphere. Jupiter's moons present a fascinating study in the influence of tidal heating on otherwise frigid worlds. Io, the innermost large moon, experiences such intense tidal flexing due to Jupiter's gravitational pull that it has become the most volcanically active body in the solar system, with surface temperatures that can reach an uncold positive 1400 degrees Celsius near its volcanic vents. In stark contrast, Jupiter's outermost large moon Callisto receives minimal tidal heating and has a surface temperature of about negative 150 degrees Celsius. Europa, perhaps Jupiter's most intriguing moon, has a surface temperature of negative 160 degrees Celsius, but likely harbors a global subsurface ocean kept liquid by tidal heating. This makes Europa one of the most promising places to search for extraterrestrial life in our solar system. The cold surface ice, estimated to be 15 to 25 kilometers thick, protects the ocean below from radiation and vacuum, while potentially allowing nutrients from the surface to cycle into the waters below through cracks in the ice. Moving to Saturn, we find a world emblematic of the beauty that cold can create. Saturn's magnificent rings, spanning up to 280,000 kilometers from edge to edge, but only about 10 meters thick in most places, consist primarily of water ice particles, ranging in size from microscopic dust to house-sized boulders. These rings maintain temperatures between -163 and -193 degrees Celsius, cold enough that the ice behaves like rock, retaining the crisp, defined structure that makes Saturn's rings so striking. Saturn's largest moon, Titan, presents one of the most Earth-like yet alien environments in our solar system. With a surface temperature of -179 degrees Celsius, it is far too cold for liquid water. Yet Titan has a thick atmosphere, clouds, rain, rivers, and seas, all composed primarily of methane and ethane, hydrocarbons that remain liquid at these frigid temperatures. Titan essentially recreates Earth's hydrological cycle with different materials, demonstrating how cold can create familiar processes with exotic components. Even more remarkable is Saturn's smaller moon Enceladus, where geysers of water vapor erupt from cracks near the South Pole, suggesting a subsurface ocean similar to Europa's. The surface temperature of Enceladus is an extreme -198 degrees Celsius, yet the plumes of water ice particles indicate substantial liquid water beneath the surface, again maintained by tidal heating. The material ejected from these geysers eventually forms Saturn's E-ring, creating a visible connection between the Moon and its parent planet. As we continue to the outer solar system, we reach Uranus and Neptune, often called the ice giants due to their composition of mostly water, methane, and ammonia ices surrounding relatively small rocky cores. Uranus holds the distinction of being the coldest planet in our solar system, with cloud-top temperatures reaching as low as -224 degrees Celsius. This extreme cold results partly from Uranus's unusual axial tilt of about 98 degrees, which causes it to effectively roll around the Sun on its side, creating extreme seasonal variations. Neptune, despite being farther from the Sun, is actually slightly warmer than Uranus, with minimum temperatures of about -214 degrees Celsius. This unexpected warmth comes from internal heat, as Neptune radiates 2.6 times more energy than it receives from the Sun. This internal heating drives some of the most violent weather in the solar system, with wind speeds reaching 2,000 kilometers per hour, faster than the speed of sound on Earth. Both Uranus and Neptune have fascinating moons that exhibit their own cold characteristics. Triton, Neptune's largest moon, has a surface temperature of about -235 degrees Celsius, making it one of the coldest objects in the solar system. Despite this extreme cold, Triton shows evidence of cryovolcanism, with eruptions of liquid nitrogen, dust, or methane, rather than the molten rock of conventional volcanoes. These eruptions create plumes that rise up to 8 kilometers before depositing dark material on the moon's icy surface. Triton also has the distinction of being one of the few objects in the solar system with a retrograde orbit, meaning it orbits in the opposite direction of Neptune's rotation. This suggests that Triton was captured from the Kuiper Belt, the region of icy bodies beyond Neptune, rather than forming alongside Neptune. This capture would have dramatically affected Triton's original orbit, creating tidal forces that likely melted much of its interior and continue to provide some heating today. Beyond Neptune lies the realm of dwarf planets and Kuiper Belt objects, a region of countless icy bodies orbiting in the dim twilight of the distant Sun. Pluto, once considered the 9th planet and now classified as a dwarf planet, has a surface temperature of approximately -230 degrees Celsius. NASA's New Horizons spacecraft revealed Pluto to be a surprisingly active world, with nitrogen ice glaciers flowing from highlands into a vast heart-shaped plain known as Sputnik Planitia. The extreme cold of Pluto allows for a remarkably diverse landscape of frozen volatiles. Nitrogen, methane, and carbon monoxide ices sublimate and redeposit across Pluto's surface as it moves through its highly elliptical orbit, creating seasonal variations despite the distant, faint sun. Mountains of water ice, which at Plutonian temperatures behaves like rock, rise up to 3.5 kilometers high, some capped with methane snow that has a reddish hue due to interaction with solar radiation. Other dwarf planets in the outer solar system show similar cold-induced features. Eris, slightly smaller than Pluto, but more massive due to its higher density, has a surface likely dominated by nitrogen ice at temperatures estimated to be around -230 to -240 degrees Celsius. Makemake and Haumea similarly have surfaces of frozen methane, ethane, and other hydrocarbons, creating a family of worlds where substances that are gases on Earth become the rock and ice of alien geology. As we approach the edge of our solar system, we reach the Oort Cloud, a spherical shell of icy bodies thought to extend up to 1 light-year from the Sun. These distant objects, consisting primarily of water, ammonia, and methane ices, exist at temperatures barely above the background temperature of space itself, around 4 Kelvin. This extreme cold preserves these bodies in nearly pristine condition, maintaining a record of the materials from which our solar system formed over 4.5 billion years ago. The cold worlds of our solar system demonstrate the extraordinary diversity that can emerge under different temperature regimes. From the familiar hydrological cycles of Earth to the methane rivers of Titan, from the nitrogen glaciers of Pluto to the cryovolcanoes of Triton, cold shapes planetary processes in ways both familiar and alien. These diverse environments expand our understanding of what might be possible on exoplanets orbiting other stars, where an even wider range of conditions likely exists. Our exploration of cold places in the solar system also challenges our understanding of habitability and the potential for life. The discovery of subsurface oceans on worlds like Europa and Enceladus suggests that life might exist in environments far colder than previously thought possible, sheltered beneath ice shells but warmed by tidal or radioactive heating. Even in environments too cold for liquid water, alternative biochemistries based on liquid methane or ethane, as might exist on Titan, cannot be ruled out. The study of cold environments in our solar system has practical implications for human exploration as well. The water ice in lunar polar craters and Martian subsurface deposits represents not just scientific interest, but potential resources for future astronauts. The extreme cold of these environments presents challenges for human habitation and equipment operation, but also opportunities for in situ resource utilization that could make sustainable presence beyond Earth possible. As we conclude our tour of the coldest places in our solar system, we can appreciate how cold, far from being simply the absence of heat, actively shapes the evolution and current state of the worlds around us. From the familiar landscapes of Earth's polar regions to the exotic terrains of dwarf planets at the solar system's edge, cold creates conditions both challenging and conducive to the processes that make planets dynamic, evolving systems. Even in our own backyard, the cosmos breathes cold into every corner. Our journey through the coldest places in the universe now takes us beyond the boundaries of our solar system, into the vast darkness between the stars. Here, drifting silently through interstellar space, are some of the most isolated and frigid worlds imaginable. These are the rogue planets, celestial wanderers that travel through the cosmos without a parent star to provide warmth and light. Unmoored and alone, these nomadic worlds experience a perpetual night and cold beyond anything found on planets orbiting stars. Rogue planets, also called free-floating planets or interstellar planets, were once the stuff of theoretical speculation. Astronomers reasoned that during the chaotic early stages of planetary system formation, some planets might be ejected from their birth systems through gravitational interactions with larger planets or passing stars. These unfortunate worlds would then be flung into interstellar space, destined to wander the galaxy in darkness. For decades, this remained an intriguing hypothesis without direct observational evidence. In recent years, however, astronomers have found compelling evidence for the existence of these cosmic orphans. Using innovative observational techniques like gravitational microlensing, where a planet's gravity temporarily magnifies the light from a distant background star, researchers have detected several candidates for rogue planets. Some estimates suggest that free-floating planets might actually outnumber stars in our galaxy, with potentially billions or even trillions of these dark, cold worlds drifting through the Milky Way. The temperatures on rogue planets represent some of the most extreme cold environments for substantial bodies in the universe. Without a nearby star to provide heat, these worlds cool inexorably toward the background temperature of interstellar space, approximately 2.7 Kelvin. However, they never quite reach this ultimate cold. Even rogue planets have internal sources of heat that, while minimal, prevent them from cooling completely to the cosmic background. The primary source of internal heat for rogue planets depends on their size and composition. Large gaseous rogue planets, similar in composition to Jupiter or Neptune, experience heating from gravitational contraction, a slow but continuous process where gravity pulls the planet's material inward, converting gravitational potential energy into heat. This process, while inefficient, can maintain internal temperatures sufficient to prevent the complete freezing of a gas giant's core for billions of years. Rocky rogue planets, more similar to Earth, experience a different form of internal heating. Radioactive elements like uranium, thorium, and potassium, incorporated into the planet during its formation, decay over time, releasing energy that heats the planet from within. On Earth, this radiogenic heating contributes only modestly to our energy budget, overwhelmed by the sun's contribution. But on a rogue planet, this feeble internal heat becomes the dominant energy source, providing a bare minimum of warmth in an otherwise frigid existence. The surface conditions on a rogue planet would be almost unimaginably alien compared to any world in our solar system. Without a star to create day and night cycles, time would have little meaning. Eternal darkness would prevail, broken only by the faint light of distant stars and perhaps aurorae. If the planet maintained a magnetic field, the temperature would be remarkably uniform across the entire surface, with no warm equator or cold poles, no seasons, and minimal weather patterns in any atmosphere that managed to persist. For a rocky rogue planet, the surface temperature might stabilize around 30 to 40 Kelvin, or about negative 230 degrees Celsius. At this extreme cold, any water would be frozen harder than concrete, and gases like nitrogen and oxygen would have long since condensed into liquids or solids. The surface might be covered with exotic forms of ice or cold-trapped atmospheric components, creating a landscape utterly unlike anything we experience on Earth. A gas giant rogue planet would maintain a somewhat warmer interior, with temperatures increasing dramatically toward the core. While its upper atmosphere might be extremely cold, perhaps 50 to 60 Kelvin, the temperature would rise with depth due to the increasing pressure. The core itself might maintain temperatures of several thousand Kelvin, surprisingly hot given the planet's isolation. This temperature gradient would drive convection currents within the planet's fluid interior, potentially maintaining a magnetic field through a dynamo effect similar to Earth's. One of the most fascinating aspects of rogue planets is the possibility that some might harbor subsurface oceans despite their extreme external cold. The internal heat from radioactive decay or tidal flexing, if the rogue planet has large moons, could be sufficient to maintain liquid water beneath a thick ice shell. This scenario is not as far-fetched as it might initially seem, as we already know of several moons in our solar system, like Europa and Enceladus, that have subsurface oceans maintained primarily by internal heat rather than solar warming. This possibility raises the intriguing question of whether life could exist on or within rogue planets. At first glance, the prospects seem bleak. Without stellar energy to drive photosynthesis, the foundation of most Earth ecosystems, what energy source could sustain biology? Yet life on Earth has demonstrated remarkable adaptability, with ecosystems discovered around hydrothermal vents in the deep ocean that derive energy entirely from chemical reactions independent of sunlight. Similar chemosynthetic ecosystems might theoretically exist in the subsurface oceans of rogue planets. The potential habitability of rogue planets depends critically on their history before ejection from their original star systems. A planet that formed and evolved with a parent star for hundreds of millions of years before being ejected might have already developed life. Such organisms would face a severe evolutionary challenge as their world cooled, but might adapt by migrating to subsurface environments where geothermal energy could sustain them. A planet ejected early in its formation, by contrast, might never develop the conditions necessary for life to emerge. For gas giant rogue planets, any potential for habitability would likely reside not on the planet itself, but on its moons, should it have retained them during ejection. These moons could experience tidal heating as they orbit the planet, creating warm regions in an otherwise cold environment. This tidal energy comes from the flexing of the moon as it moves through the planet's gravitational field, converting orbital energy into heat. The effect is especially pronounced when multiple moons create resonant orbits, as seen with Jupiter's moons Io, Europa, and Ganymede. The dynamics of a moon system around a rogue planet would evolve differently than around a planet orbiting a star. Without solar radiation pressure or third body effects from a nearby star, the orbits might remain stable for extraordinarily long periods. However, the absence of external energy input would mean that any tidal heating would gradually diminish as the system evolved toward the lowest energy state. Over billions of years, the moons would either impact the planet, escape the system, or settle into circular, equatorial orbits that minimize tidal interactions. Detecting and studying rogue planets presents enormous challenges for astronomers. These objects emit virtually no visible light of their own and reflect no starlight, making them nearly invisible to conventional telescopes. The most successful detection method has been gravitational microlensing, where the gravity of a rogue planet briefly magnifies the light from a background star as the planet passes in front of it. These events are rare and short-lived, typically lasting only days or weeks, requiring constant monitoring of millions of stars to catch the telltale brightening. More recent detection efforts have focused on infrared observations, as even cold rogue planets emit some thermal radiation at long wavelengths. The James Webb Space Telescope, with its extraordinary sensitivity to infrared light, offers new opportunities to directly detect these wandering worlds. Young rogue planets, still warm from their formation, emit enough infrared radiation to be potentially observable, especially if they are relatively close to our solar system. Several candidate rogue planets have generated particular interest among astronomers. One, designated OJUL 2018 BLG 0799, appears to be an object between the size of Earth and Neptune drifting through the galaxy. Another, PSOJ 318.5-22, seems to be a gas giant about 6 times the mass of Jupiter, young enough that it still glows faintly in infrared light from the heat of its formation. These and other detections suggest that rogue planets span the full range of planetary types, from small rocky worlds to massive gas giants. The origin of rogue planets remains an active area of research. While many were likely ejected from forming planetary systems through gravitational interactions, some may have formed directly from the collapse of small knots of gas and dust in stellar nurseries, too small to ignite as stars, but able to condense into planet-sized objects. Others might result from the disruption of binary star systems, where one star captures the planets of the other before the stars separate. Each formation pathway would leave distinctive imprints on the rogue planet's composition and structure. The ultimate fate of these wandering worlds is equally fascinating to consider. Most will likely drift through interstellar space indefinitely, gradually cooling over trillions of years until they reach nearly the same temperature as the cosmic background radiation. Some may be recaptured by passing stars, finding themselves in new orbital arrangements after billions of years of solitary travel. Others might eventually fall into the central regions of the galaxy, where the density of stars is higher, increasing both their chances of capture and the risk of destructive collisions. In the most extreme cases, a rogue planet might be gravitationally captured by a black hole, either a stellar mass black hole formed from a collapsed star, or one of the supermassive black holes found at the centers of galaxies. Such a planet would likely be torn apart by tidal forces as it approached, its material forming a brief, bright accretion disk before disappearing beyond the event horizon. This spectacular end would ironically make the planet momentarily visible as it was destroyed, a final flash of energy after eons of darkness. The total number of rogue planets in our galaxy remains highly uncertain, with estimates ranging from hundreds of billions to as many as trillions. If the higher estimates prove correct, rogue planets could outnumber stars by a significant margin, making them the most common type of substantial object in the Milky Way. This possibility challenges our star-centered view of the galaxy and suggests that much of its mass exists in perpetual darkness, unseen and difficult to detect. The cold of rogue planets might seem uniformly hostile to life as we know it, but these worlds likely represent a diverse population with varying histories and characteristics. Some may have formed and evolved around stars for billions of years before being ejected, potentially allowing complex life to develop before beginning their interstellar journey. Others might have been ejected as embryonic protoplanets, never experiencing the warmth of a star. This diversity suggests that we should be cautious about generalizing about conditions on these nomadic worlds. One intriguing possibility is that some rogue planets might retain substantial atmospheres despite their isolation and cold. Gas giants, with their strong gravitational fields, could hold on to hydrogen and helium atmospheres essentially indefinitely. Super-Earth-sized rogue planets might maintain denser atmospheres of heavier gases like nitrogen for billions of years. These atmospheres would become physically peculiar in the extreme cold, potentially condensing or freezing in layers, with only the highest pressure regions near the surface remaining gaseous. For rocky rogue planets, any water present during formation would quickly freeze on the surface, potentially creating ice layers kilometers thick. In the extreme cold of interstellar space, this ice would be rock hard and would actually help insulate the planet's interior, trapping the meager heat from radioactive decay. Beneath this frozen crust, the rocky interior might remain warm enough for underground water to persist in liquid form, creating potential habitats for extremophile organisms. The discovery and characterization of rogue planets represent a frontier in modern astronomy. Each detection provides new insights into the dynamics of planetary system formation and evolution, the mechanisms of planetary ejection, and the frequency of planetary bodies in our galaxy. As detection technologies improve, particularly with infrared observatories like the James Webb Space Telescope, we can expect our census of these dark worlds to grow rapidly in the coming decades. The cold, dark, isolated nature of rogue planets might make them seem like cosmic dead ends, failed worlds ejected from the systems where they formed. Yet from another perspective, these wandering planets represent an astonishing possibility for the dispersal of life throughout the galaxy. If a rogue planet harboring life were ejected from its home system, it could theoretically transport that life across interstellar distances, serving as a natural generation ship drifting between stars. While such life would need to survive on internal energy sources alone, deep subsurface environments might provide sufficient warmth and chemical energy to sustain simple ecosystems for billions of years. This possibility connects to the concept of panspermia, the hypothesis that life might be distributed throughout the universe by hitchhiking on asteroids, comets, or other celestial bodies. Rogue planets represent a particularly intriguing vector for such distribution, as they could potentially carry entire ecosystems rather than just dormant spores or simple organisms. While highly speculative, this scenario suggests that the cold wanderers of interstellar space might play an unexpected role in the development and dispersal of life in the cosmos. The technology needed to detect and study rogue planets will continue to advance in the coming years. Future space telescopes with even greater sensitivity than the James Webb may be able to directly image nearby rogue planets in infrared light, revealing details of their size, composition, and temperature. More extensive microlensing surveys, potentially conducted from space to avoid atmospheric interference, could provide a more complete census of these objects throughout the galaxy. As we continue to study these cold, dark worlds, we expand our understanding of the diverse environments that exist in our universe. The rogue planets drifting in eternal night remind us that planets need not be warm, sunlit worlds like our own to be fascinating objects worthy of study. They represent an entirely different mode of planetary existence, one defined by isolation, darkness, and extreme cold, rather than the warmth and light that sustain life on Earth. No sunrise ever warms them, but still, they exist, alone in the dark. Our journey through the coldest places in the universe returns to our own solar system, where we explore in greater depth the frozen realms of the ice giants and their moons. Uranus and Neptune, the seventh and eighth planets from our Sun, represent a distinct class of worlds different from both the rocky inner planets and the gas giants Jupiter and Saturn. These ice giants, along with their diverse satellite systems, offer fascinating examples of cold worlds where exotic forms of ice shape entire planetary systems. Uranus, discovered in 1781 by William Herschel, orbits the Sun at an average distance of 2.9 billion kilometers, receiving only 1/400th the sunlight that reaches Earth. This faint warming, combined with Uranus's unique orientation, creates one of the coldest planetary atmospheres in our solar system. Uranus rotates on its side, with its axis tilted by 98 degrees relative to its orbit, causing it to effectively roll around the Sun. This extreme tilt, likely the result of a massive collision early in the planet's history, creates seasonal extremes unlike anything else in our solar system. The atmosphere of Uranus consists primarily of hydrogen and helium, similar to Jupiter and Saturn, but with a much higher proportion of ices, including water, ammonia, and methane. It is this latter component, methane, that gives Uranus its distinctive pale blue-green color, as methane gas absorbs red light while reflecting blue and green wavelengths back to our telescopes. Below this atmospheric layer lies the true nature of the ice giant, a vast mantle of exotic water, ammonia, and methane ices surrounding a relatively small rocky core. The term ice in this context requires some clarification. These are not the crystalline forms of ice familiar to us on Earth's surface, but rather hot, dense, and often fluid phases that exist under the extreme pressures and temperatures within the planet. Scientists sometimes refer to these materials as ices because they formed from compounds that are volatile in the outer solar system, like water, ammonia, and methane, as opposed to the rocky materials that make up the inner planets. The temperature in Uranus's cloud tops reaches as low as negative 224 degrees Celsius, making it colder than Neptune despite being closer to the Sun. This anomaly results from Uranus's low internal heat. Unlike the other giant planets, which radiate significantly more energy than they receive from the Sun, Uranus emits barely any excess heat. The reasons for this thermal deficit remain mysterious, but may relate to the ancient impact that tilted the planet, potentially disrupting its internal circulation and heat transport mechanisms. Despite its frigid nature, Uranus possesses a dynamic atmosphere with seasons that last 21 Earth years. During the Voyager 2 flyby in 1986, the South Pole was facing the Sun, and the planet appeared relatively featureless. Subsequent observations with advanced telescopes have revealed that as other regions receive sunlight, storm systems develop and evolve, showing that even at these extreme temperatures, weather occurs in the ice giant's atmosphere. Recent observations have detected massive storms comparable in size to North America, suggesting that the planet's atmosphere is more active than initially thought. Beneath the visible clouds likely lies a structure quite different from the gas giants. Rather than a clear distinction between atmosphere and interior, Uranus probably has a more gradual transition, with the atmospheric gases becoming increasingly dense and hot with depth, until they merge with the fluid icy mantle below. This mantle, composed primarily of water, ammonia, and methane under high pressure and temperature, extends to a depth of approximately 80% of the planet's radius, surrounding a small rocky core. One of the most intriguing features of Uranus is its magnetic field, which is tilted by 59 degrees from the planet's rotational axis and offset from the center. This unusual configuration, unlike the more aligned magnetic fields of Earth and Jupiter, suggests that the field is generated not in a metallic core, but in a shallow, electrically conducting layer of exotic water ice. Under the extreme pressures within Uranus, water molecules break down, allowing the oxygen and hydrogen atoms to conduct electricity and generate a magnetic field through a dynamo effect. The cold of Uranus extends to its ring system, a subtle set of narrow bands, first definitively detected in 1977. Unlike Saturn's bright icy rings, those of Uranus are dark and narrow, composed of particles ranging from dust size to several meters, likely carbonaceous material with a low reflectivity. The extreme cold at Uranus's distance from the Sun allows these delicate structures to remain stable, as there is minimal solar radiation pressure to disrupt the orbits of the ring particles. Orbiting beyond the rings are Uranus's 27 known moons, a diverse collection of worlds all experiencing the profound cold of the outer solar system. 5 major moons, Titania, Oberon, Umbriel, Ariel, and Miranda, offer the most intriguing glimpses into cold world geology. These moons, composed primarily of roughly equal parts rock and water ice, have surface temperatures of approximately negative 187 degrees Celsius, cold enough that water ice behaves like rock, allowing for the formation of mountains, canyons, and other geological features. Miranda, the innermost and smallest of the major moons, displays some of the most dramatic terrain in the solar system despite its small size. just 472 kilometers in diameter. Its surface includes features nicknamed coronae, huge oval-shaped regions with concentric ridges and valleys, alongside cliffs that soar up to 20 kilometers high. This chaotic terrain suggests a violent past, possibly including a catastrophic disruption and reassembly of the Moon early in its history. At Miranda's frigid temperatures, the water ice that comprises about half its mass behaves mechanically like stone, allowing these extreme topographic features to remain stable for billions of years. Moving outward from Uranus, we encounter Neptune, the most distant of the solar system's major planets, orbiting at an average distance of 4.5 billion kilometers from the Sun. Despite receiving only 40% of the already feeble sunlight that reaches Uranus, Neptune paradoxically has a warmer upper atmosphere, with temperatures around -214 degrees Celsius. This relative warmth comes from Neptune's substantial internal heat source, as the planet radiates 2.6 times more energy than it receives from the Sun. Neptune's blue color, deeper and more vivid than Uranus's pale cyan, results from the same methane absorption of red light, but additional unknown components in its atmosphere enhance this effect. Beneath the visible clouds, Neptune likely has a structure similar to Uranus, with a thick mantle of hot, dense water, ammonia, and methane ices surrounding a rocky core. The higher internal heat creates a more dynamic atmosphere, with the fastest winds in the solar system reaching speeds of 2,100 kilometers per hour, more than 1.5 times the speed of sound on Earth. The extreme winds drive dramatic weather on Neptune, including the famous Great Dark Spot observed by Voyager 2 in 1989, a storm system comparable in size to Earth. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's dark spots are transient features, forming and dissipating over periods of years. The rapid evolution of these storm systems demonstrates that even in the cold outer solar system, significant atmospheric dynamics occur, driven by the combination of internal heat and the planet's rapid rotation of about 16 hours. Like Uranus, Neptune possesses a magnetic field, tilted relative to its rotational axis, in this case by 47 degrees. This similarity suggests that the magnetic fields of both ice giants are generated not in their cores, but in shallower regions of electrically conducting fluid. The extreme pressures and temperatures within these planets create exotic states of matter, where substances that are familiar gases or ices on Earth behave in counterintuitive ways, including becoming electrically conductive while remaining fluid. Neptune's ring system, first definitively detected in 1989 during the Voyager 2 flyby, consists of several faint, narrow rings with unusual clumpy structures. Unlike the relatively stable rings of Saturn, Neptune's rings are dynamic and evolving, with concentrations of material that astronomers call ring arcs. These arcs remain stable against orbital dispersion due to gravitational resonances with the moon Galatea, demonstrating how complex gravitational interactions can maintain structures even in the cold, distant reaches of the solar system. Among Neptune's 14 known moons, Triton stands out as one of the most fascinating objects in the entire solar system. With a diameter of 2,710 kilometers, it is the 7th largest moon in the solar system and the only large moon with a retrograde orbit, moving around Neptune in the direction opposite to the planet's rotation. This backward orbit strongly suggests that Triton is a captured object, originally a dwarf planet from the Kuiper Belt that ventured too close to Neptune and was gravitationally trapped. The surface of Triton is one of the coldest places measured in our solar system, with temperatures of approximately -235 degrees Celsius. This extreme cold results from the combination of Triton's distance from the Sun and its highly reflective surface, which absorbs minimal solar radiation. The surface consists primarily of nitrogen ice, with smaller amounts of methane and carbon dioxide ices, creating a landscape utterly alien compared to rocky or water ice-dominated worlds. Despite these frigid conditions, Voyager 2 observed active nitrogen geysers on Triton's surface, making it one of only 4 bodies in the solar system, along with Earth, Enceladus, and Io, known to be geologically active at the time of discovery. These geysers erupt from the subsurface, sending plumes of nitrogen gas and dark dust particles up to 8 kilometers high before the material settles back to the surface, creating dark streaks across the brightly opacified terrain. This activity likely results from subsurface heating, possibly from tidal forces or radiogenic heating, coupled with a greenhouse effect where transparent nitrogen ice allows sunlight to warm darker material below. The geysers contribute to Triton's unique atmosphere, an extraordinarily thin layer of nitrogen and methane with a surface pressure only about 1/70,000th that of Earth. This tenuous atmosphere undergoes seasonal changes as nitrogen and methane cycle between gas and solid phases, with Triton's 165-year orbit around the Sun. The cold is so intense that even nitrogen, which remains gaseous at Earth's Arctic temperatures, freezes solid on Triton's surface. The surface features of Triton reflect its cold-driven processes. Large areas show a texture nicknamed cantaloupe terrain, a complex pattern of depressions thought to result from the convection of nitrogen ice or the eruption of a water-ammonia slurry from below. Other regions display nitrogen ice sheets that flow like glaciers, despite the extreme cold. These flows remain possible because even though nitrogen ice is very cold, it exists near its melting point at Triton's surface conditions, allowing for slow deformation and flow over geological timescales. The ice giants and their moons represent a distinct class of cold worlds where the low temperatures and unique compositions create conditions unlike anything on Earth. On these worlds, substances that are gases in our everyday experience become the rocks and working fluids of alien geologies. Methane and nitrogen, familiar components of our atmosphere, form the ice mountains and glaciers of these distant moons. Water ice, so readily melted on Earth, becomes as hard as granite, forming the bedrock of entire worlds. Beyond the major moons we've discussed, the ice giants host numerous smaller satellites, each a frozen world in its own right. These smaller moons, many just tens of kilometers across, have never been visited by spacecraft and remain mysterious. Their sizes suggest they are likely not massive enough to have experienced significant geological evolution and probably represent primordial bodies preserved in the deep freeze of the outer solar system since the formation of the planets. The ring systems of the ice giants also deserve further consideration as cold environments. The individual particles, ranging from dust-sized grains to boulder-sized chunks, experience surface temperatures similar to the planet they orbit, around -220 degrees Celsius. At these temperatures, any water ice components are rock hard, while more volatile ices like methane or carbon monoxide might periodically sublimate and redeposit, creating a subtle cycle of material within the ring systems. The origin of the ice giants themselves remains somewhat mysterious. Standard models of solar system formations struggle to explain how planets as massive as Uranus and Neptune formed at their current distances from the Sun, where the protoplanetary disk would have been quite thin. Some theories suggest they formed closer to the Sun and migrated outward, while others propose rapid formation by direct collapse from the solar nebula. The answer to this puzzle likely holds important clues to understanding the prevalence and nature of similar planets around other stars. Indeed, exoplanet surveys suggest that ice giant-sized worlds may be among the most common types of planets in our galaxy. The Kepler mission and other surveys have detected numerous planets with radii between those of Earth and Neptune, a size class not represented in our solar system. Many of these worlds likely have compositions similar to our ice giants, although often orbiting much closer to their stars. This context makes our own ice giants valuable archetypes for understanding a major class of planets throughout the cosmos. Future exploration of the ice giants and their moons would revolutionize our understanding of these cold worlds. Unlike Jupiter and Saturn, which have been studied by multiple dedicated missions including Galileo, Juno and Cassini, the ice giants have received only brief flybys from Voyager 2. The limited data from these encounters, while invaluable, leaves many questions unanswered about the interior structure of the planets, the composition and dynamics of their atmospheres, and the geology and potential subsurface oceans of their moons. Various space agencies have proposed dedicated missions to Uranus or Neptune, including orbiters that would study the planets and their moons in detail. Such missions would likely reveal entirely new aspects of cold world processes, potentially including active geology on moons beyond Triton, details of the planet's unusual magnetic fields, and insights into the mysterious lack of internal heat from Uranus. The technical challenges are formidable, given the extreme distances involved, but the scientific rewards would be enormous. One of the most intriguing possibilities for future exploration involves searching for subsurface oceans on the larger moons of Uranus and Neptune. Models suggest that moons like Titania, Oberon and Ariel might maintain liquid water layers between their icy crusts and rocky cores, heated by a combination of tidal forces and radioactive decay. These oceans, if they exist, would represent potential habitats for extraterrestrial life, adding the ice giant systems to the growing list of solar system locations where life might potentially exist. The potential for habitability extends even to frigid Triton, where the evidence of ongoing geological activity suggests internal heat sources that might maintain a subsurface water ocean. The observed geysers, while composed primarily of nitrogen, might include traces of material from any subsurface ocean, making them accessible to sampling by future spacecraft without the need to drill through the outer ice shell. Similar considerations apply to Pluto, which shows surprising geological activity, despite surface temperatures comparable to Triton's. As we contemplate these distant, frigid worlds, we gain perspective on the relationship between cold and life in the cosmos. The conventional habitable zone concept focuses on planets where surface water can remain liquid, but the outer solar system teaches us that habitability might extend much further through the mechanism of subsurface oceans. If life exists in such environments, it would need to function without photosynthesis, relying instead on chemosynthesis powered by geological processes, similar to ecosystems around deep-sea vents on Earth. The cold of the ice giants and their moons also preserves a record of solar system history that has been erased on warmer worlds. The low temperatures drastically slow chemical reactions and physical processes that would quickly modify surfaces closer to the Sun. By studying these preserved worlds, we gain insights into the conditions and materials that existed when the solar system formed, allowing us to reconstruct the processes that led to our current planetary arrangements. The extreme cold of these distant worlds creates environments where the familiar becomes exotic and the exotic becomes familiar. Water, the fluid so central to life on Earth, becomes the bedrock upon which mountains form. Nitrogen and methane, mere trace gases in our atmosphere, become the working substances of alien geologies. Even gravity seems to have different implications, as materials we consider firm on Earth behave as viscous fluids over geological timescales in these frigid environments. This transformation of the familiar into the alien through the action of cold reminds us of the diversity possible even within the constraints of physical laws. The same substances subjected to different conditions create worlds of remarkable variety. The ice giants and their moons, though composed of elements common throughout the solar system, arrange these building blocks into configurations dictated by the profound cold of their environments, creating landscapes and processes with no direct Earth analogues. As our journey through the coldest places in the universe continues, the ice giants and their frozen moons stand as examples of how cold shapes entire planetary systems, creating dynamic, evolving worlds despite the extreme low temperatures. They remind us that cold does not necessarily mean static or lifeless, that even in the most frigid environments, energy can find expression through processes uniquely adapted to these conditions. Frozen worlds may seem lifeless, but sometimes the cold protects more than it destroys. Our journey through the coldest places in the universe now takes us beyond the present and into the distant future. Having explored natural cold in cosmic voids, molecular clouds and planetary systems, and the artificial cold created in Earth's laboratories, we now turn to what may be the ultimate cold, the thermal fate of the entire cosmos. The future we contemplate stretches almost beyond imagination, encompassing timescales so vast that they make the current age of the universe seem like the briefest moment in comparison. The evidence from modern cosmology points toward a universe that is not only expanding, but accelerating in its expansion, driven by a mysterious force scientists call dark energy. This acceleration has profound implications for the thermal future of the cosmos. As space stretches ever faster, galaxies beyond our local group will eventually recede so rapidly that their light can never reach us. The observable universe will gradually empty, leaving our Milky Way and its nearest neighbors isolated in an increasingly vast and empty cosmos. This accelerating expansion leads cosmologists to a scenario known as the Big Freeze or heat death, the most widely accepted model for the universe's ultimate fate. In this vision of the cosmic future, the universe does not collapse back on itself in a big crunch, nor does it tear itself apart in a big rip. Instead, it expands forever, growing progressively colder, darker, and more diffuse until it reaches a state of maximum entropy, where no further work is possible and all energy has been evenly distributed across an effectively infinite volume of space. To understand this cold future, we must follow the timeline of cosmic evolution far beyond the present day. Our journey begins in the relatively near astronomical future, just a few billion years from now, when our Milky Way galaxy collides and merges with the neighboring Andromeda galaxy. This merger, already set in motion by gravitational attraction, will transform our home galaxy and night sky, but represents merely the first step in a much longer process of cosmic evolution. By about 100 billion years from now, the accelerating expansion of space will have carried all galaxies beyond our local group to such distances that they become invisible, even to the most powerful conceivable telescopes. The light from these distant galaxies, stretched by the expanding space it travels through, will be redshifted to wavelengths too long to detect. An observer in this far future would see only a small collection of merged galaxies surrounded by absolute darkness, with no observational evidence of the broader cosmos that once existed. This isolation begins what astronomers call the degenerate era, spanning from approximately 100 billion to 100 trillion years from now. During this unimaginably long period, normal stars like our Sun will have long since exhausted their nuclear fuel. The universe will grow increasingly dark, illuminated only by the feeble glow of red and brown dwarf stars, which burn their fuel so slowly that some may last for trillions of years before finally flickering out. As even these long-lived stars eventually exhaust their fuel, they will cool to become black dwarfs, the completely cold and dark remnants of stars too small to explode as supernovae. Unlike white dwarfs, which still radiate residual heat from their stellar lifetimes, black dwarfs will have cooled to equilibrium with the cosmic background radiation, becoming essentially invisible in the darkness of deep time. Meanwhile, the supermassive black holes at the centers of galaxies will continue to grow by consuming nearby stars and gas. But this process becomes increasingly inefficient as material becomes scarcer. These black holes will dominate the energy production of the future universe, converting matter to energy more efficiently than stars ever could, but with increasingly less material to consume. The radiation from matter falling into black holes will provide brief flashes of light in an otherwise darkening cosmos. By the end of the degenerate era, roughly 100 trillion years from now, conventional astronomical objects will have largely disappeared. Stars will have burned out, planets will have been ejected from their systems or spiraled into stellar remnants, and galaxies will have either merged or been torn apart by gravitational interactions. The universe will consist primarily of black holes, neutron stars, and black dwarfs scattered across an ever-expanding void. This sets the stage for the black hole era, extending from approximately 100 trillion to 100 quintillion years from now. During this era, black holes become the dominant objects in the universe. They slowly radiate energy through a quantum process known as Hawking radiation, named after physicist Stephen Hawking, who first described it theoretically. This radiation occurs when virtual particle pairs form near the black hole's event horizon, with one particle falling in and the other escaping, effectively extracting energy from the black hole itself. For stellar mass black holes, this evaporation process is extraordinarily slow, requiring roughly 10 to the power of 67 years for complete evaporation. Supermassive black holes, with masses millions or billions of times greater than our Sun, will last even longer, up to 10 to the power of 100 years. During this era, the occasional collision between neutron stars or black holes might briefly illuminate the darkness with gravitational waves and electromagnetic radiation. But such events become increasingly rare as distances between objects grow. As black holes radiate away their mass through Hawking radiation, they shrink in size and their temperature actually increases. In the final moments of a black hole's existence, it releases a burst of high-energy radiation, a final flash before disappearing completely. These rare events will provide the only significant energy production in an otherwise cold and dark universe. Eventually, even the largest black holes will evaporate. leading to the dark era beginning approximately 100 quintillion years from now. In this final age of the universe, conventional matter will have largely disappeared. Protons, the building blocks of atomic nuclei, may have decayed through processes predicted by some extensions of the standard model of particle physics, though this remains theoretically uncertain. If proton decay occurs, the universe will consist primarily of a dilute gas of photons, neutrinos, electrons, and positrons spread across an effectively infinite volume of space. The temperature during this era approaches absolute zero more closely than any natural environment in the current universe. As space continues to expand, the wavelength of the cosmic background radiation stretches, reducing its effective temperature well below the current 2.7 Kelvin. After googles of years, the temperature may drop to a small fraction of a nanokelvin, creating a cold so profound that it makes the chill of present-day interstellar space seem positively toasty by comparison. In this cold, dark, empty future, the concept of time itself begins to lose meaning. With no cyclical processes to mark its passage and events occurring at intervals approaching infinity, time becomes an abstract mathematical concept rather than a physically experienced phenomenon. The universe approaches what physicists call a state of thermal equilibrium, or heat death, where no further work is possible because energy has been distributed uniformly across space. Yet even in this seemingly final state, quantum mechanics suggests that the story may not be complete. According to quantum theory, random fluctuations can occur even in apparent emptiness. Given a time which the eternal expansion provides in unlimited supply, these quantum fluctuations might produce remarkable events. In principle, a random fluctuation could assemble particles into complex structures, potentially even conscious entities, though the timescales required would be so vast as to make the current age of the universe seem instantaneous by comparison. More exotic possibilities have been proposed by theoretical physicists. Perhaps the vacuum itself is not stable, but merely metastable, meaning it could eventually undergo a phase transition to a lower energy state. Such a transition would propagate through space at the speed of light, effectively rewriting the laws of physics in the regions it touches, and potentially seeding a new form of cosmic evolution. Alternatively, quantum tunneling might allow the nucleation of new baby universes, disconnected from our own, but representing a form of cosmic reproduction. These speculative outcomes remain highly uncertain, pushing against the limits of our current understanding of physics. What seems more certain is the progression toward an ever colder, ever more diffuse cosmos, where the vibrant processes that characterize our current universe gradually diminish and ultimately cease. This progression toward cold is not merely incidental, but reflects a fundamental law of thermodynamics, the inexorable increase of entropy. The heat death of the universe represents the ultimate expression of the second law of thermodynamics on a cosmic scale. This law, which states that the total entropy of an isolated system always increases over time, drives the universe from its initial low entropy state at the Big Bang toward a final high entropy state in the distant future. The cold we observe and study today, from interstellar clouds to planetary surfaces, represents intermediate stages in this grand thermodynamic journey. This connection between cold and entropy reveals something profound about the nature of cosmic evolution. The gradient from hot to cold, from concentrated energy to dispersed energy, drives all the creative processes we observe in the universe. Stars form and shine because gravity concentrates matter, creating temperature differences that fusion can exploit. Life exists on Earth because our planet absorbs concentrated energy from the sun and radiates diffuse heat back to space, using the difference to power complex chemical processes. Intelligence itself can be understood as a system that processes energy differences to create and manipulate information. In this context, the cold future of the universe represents not just an absence of heat, but the exhaustion of the energy gradients that make complexity possible. As the universe approaches uniform temperature, the capacity to sustain complexity diminishes. Structure requires energy differences to maintain itself against the tide of entropy, and in a universe of perfect thermal equilibrium, no such differences remain to be exploited. Yet there is a certain elegance, even beauty, in this final state. The heat death represents not destruction, but completion. the universe having expressed all its creative potential across unimaginable eons of cosmic evolution. From the violent energy of the Big Bang to the perfect stillness of thermal equilibrium, the cosmos will have explored the full spectrum of physical possibility, a grand cycle from order to disorder played out on the largest possible scale. This perspective suggests that the cold we observe and study is not merely an environmental condition, but a fundamental aspect of cosmic evolution. The coldest places in today's universe offer glimpses of its distant future, windows into the state toward which all of space is gradually evolving. By studying these cold environments, from molecular clouds to the cosmic microwave background, we gain insight not just into current cosmic conditions, but into the ultimate fate of everything that exists. Of course, the timescales involved in this cosmic evolution toward cold render it largely abstract from a human perspective. The stelliferous era, the current age of stars and galaxies, is expected to continue for at least another 100 billion years, thousands of times longer than the universe has existed so far. On human or even evolutionary timescales, the heat death remains so distant as to be practically irrelevant to our immediate concerns. More pressing is the thermal future of our own solar system. In about 5 billion years, our sun will exhaust the hydrogen in its core and begin to fuse helium, causing it to expand into a red giant star. This expansion will engulf the inner planets, including possibly Earth, and dramatically alter the thermal environment of the entire system. The once life-sustaining temperature of our planet will give way to incinerating heat, ending the biosphere as we know it, unless technological civilization finds means to migrate elsewhere. Following the red giant phase, the sun will shed its outer layers and contract into a white dwarf, a dense, Earth-sized remnant that will slowly cool over billions of years. Eventually, it will fade to a black dwarf, a cold, dark ember in the vastness of space. This progression from luminous star to cold remnant mirrors on a small scale the thermal evolution predicted for the universe as a whole, a journey from energy-rich activity to quiet darkness. For humans and any descendants or successor intelligences, adaptation to increasing cosmic cold seems inevitable if long-term survival is the goal. As stars burn out and useful energy becomes increasingly scarce, any continuing intelligence would need to operate with extraordinary efficiency, perhaps transitioning to substrates very different from biological ones. Some theorists have speculated about advanced civilizations hibernating during the long stretches between rare energy-producing events, awakening briefly to process information before returning to dormancy. In the far future, intelligence might need to function at extremely low temperatures to maximize efficiency, perhaps using superconducting or quantum computational substrates that actually perform better in the cold than at higher temperatures. In this way, the cold that seems hostile to life as we know it might become an enabling condition for forms of existence we can barely imagine. Intelligence adapted to harvest and process the dwindling energy of a dying cosmos with maximum efficiency. This perspective suggests a different way of thinking about cold. Rather than seeing it simply as the absence of heat, we might understand it as the canvas against which all complexity in the universe is painted. Heat represents energy in its most disordered form, while cold allows for the structured arrangements of matter that make stars, planets, and ultimately life possible. The cold future of the universe is not nothingness, but rather the final state toward which all the creative processes of the cosmos have been building. The progression toward cosmic cold also provides a framework for understanding the arrow of time itself. The fundamental distinction between past and future, absent from most equations of physics, emerges from the statistical tendency of systems to evolve from lower to higher entropy states. We remember the past and not the future because the past had lower entropy, corresponding to more organized, less probable arrangements of matter and energy. The cold future of maximum entropy represents the ultimate expression of this temporal asymmetry, the final destination toward which the arrow of time points. This connection between cold, entropy, and time suggests that our intuitive discomfort with extreme cold may reflect something fundamental about our nature as complex, entropy-producing systems. Life as we know it exists by maintaining internal order against the tide of entropy, consuming concentrated energy and releasing dispersed waste heat. The cold of deep space, and especially the cold of the cosmic future, represents the exhaustion of the very gradients that make our existence possible. We recoil from extreme cold, not just because it threatens our biological functions, but because it symbolizes the state antithetical to the ordered complexity of life. Yet this does not mean that the cold future is without meaning or potential. The vast timescales of cosmic evolution could allow for forms of complexity and intelligence vastly different from those we currently understand. The heat death itself, while representing an end to processes familiar to us, might contain subtle forms of organization invisible from our current perspective. The quantum fluctuations mentioned earlier could, in principle, give rise to new forms of order, creating islands of complexity in the sea of cosmic uniformity. Moreover, our understanding of the universe's ultimate fate remains subject to revision as our knowledge of physics advances. The discovery of dark energy at the turn of the millennium dramatically changed cosmological predictions, shifting expectations from eventual contraction to eternal expansion. Future discoveries about the nature of dark energy, vacuum energy, or quantum gravity could similarly transform our understanding of cosmic destiny, perhaps revealing possibilities beyond the heat-death scenario. Until such revelations, the cold future remains the most scientifically supported prediction for cosmic evolution. The progression toward ever lower temperatures and ever higher entropy appears built into the fundamental laws of physics, directing the universe from its hot, dense beginning to its cold, diffuse end. This journey, spanning timescales that dwarf human comprehension, represents the grandest narrative science can currently offer, a story beginning in fire and concluding in ice. S. Eliot, who wrote, "This is the way the world ends, not with a bang, but a whimper." The heat death represents not a catastrophic conclusion, but a gentle fading, a quiet diminishment of energy differentials until nothing remains but perfect stillness. There is a certain peace in this vision, a completion that lacks the violence of alternative cosmic endings like the Big Crunch or Big Rip. For all its remoteness from human experience, the cold future of the universe provides valuable perspective on our place in cosmic history. We exist during a remarkably privileged era, when stars still shine and matter remains organized into galaxies, planets, and complex structures like ourselves. The energy gradients that make our existence possible represent a temporary condition in the grand arc of cosmic evolution, a window of opportunity for complexity that will not last forever. This realization might inspire both humility and appreciation. Humility, because our existence depends on cosmic conditions that are transient on the scale of universal history. Appreciation, because we happen to exist during the relatively brief period when conditions allow for the remarkable complexity we observe around us and embody ourselves. The cold future reminds us that the current state of the universe, with its rich structure and dynamic processes, represents a special moment in cosmic evolution. It also suggests a certain responsibility to understand and appreciate the universe during this moment of possibility. As potentially one of the few forms of matter capable of comprehending its own existence and the broader cosmos, conscious intelligence represents something remarkable. The universe evolved to the point where it can contemplate its own nature and destiny. If the cold future eventually precludes such awareness, present consciousness becomes all the more precious, a brief window when the cosmos can know itself before fading into thermal equilibrium. The study of cold thus connects the most immediate human experiences, our physical sensations of temperature and our technological achievements in refrigeration, to the grandest questions of cosmic destiny. From the artificial cold of laboratories approaching absolute zero to the natural chill of molecular clouds, from the icy surfaces of outer planets to the frigid vacuum of intergalactic space, cold reveals itself not as a single phenomenon, but as a spectrum of conditions reflecting the fundamental thermodynamic nature of the universe. Our journey through the coldest places in the universe has taken us across space and time, from the familiar cold of Earth's poles to the exotic chill of quantum condensates, from the depths of present-day interstellar space to the ultimate cold of the cosmic future. Throughout this journey, cold has emerged not merely as the absence of heat, but as a fundamental aspect of cosmic structure, a condition that both constrains and enables the processes that create complexity. As we approach the conclusion of our exploration, we might reflect on how the study of cold provides a unique window into the nature of reality itself. The cold places we have visited reveal the universe stripped to its essentials, matter and energy reduced to their most fundamental behaviors. In the clarity of extreme cold, the quantum nature of reality becomes apparent. The subtle interconnections between particles emerge, and the statistical foundations of thermodynamics reveal themselves. The cold future of the universe, with its progression toward maximum entropy and minimum temperature, represents the final expression of these fundamental principles. It reminds us that the cosmos operates according to laws that transcend human scales and concerns. Laws that direct the evolution of everything from subatomic particles to superclusters of galaxies along a common thermodynamic trajectory. The heat death, for all its remoteness from current experience, reflects the same principles that govern the more familiar cold environments we observe today. In the end, the Big Freeze represents not just a prediction about the distant future, but a statement about the fundamental nature of the cosmos. It tells us that we live in a universe governed by the inexorable increase of entropy, where energy gradually disperses and temperatures ultimately equilibrate. The cold places we study today, from quantum laboratories to interstellar clouds, offer glimpses of this ultimate state, windows into the distant future toward which all of existence slowly progresses. As conscious beings capable of understanding these processes, we occupy a unique position. We can comprehend both our origins in the hot, dense state of the early universe and our likely fate in the cold, diffuse state of the cosmic future. We exist in the middle of this great thermodynamic journey, during the remarkable period when energy gradients support the complexity necessary for awareness itself. This awareness allows us to appreciate the grand narrative of cosmic evolution, from fire to ice, from order to entropy, from concentrated potential to realized possibility. In the end, the universe will be the coldest place of all. As our journey through the coldest places in the universe draws to a close, we return to a contemplation of cold itself, not merely as a physical condition, but as a profound aspect of existence. Throughout our exploration, from the artificial chill of quantum laboratories to the natural frigidity of cosmic voids, from the ice worlds of our solar system to the ultimate cold of the far future, we have encountered cold in its many manifestations. Now, we reflect on what this fundamental state reveals about the universe and our place within it. Cold, we have discovered, is not simply the absence of heat. It is a positive presence with its own character, its own beauty, and its own role in the cosmic narrative. In the coldest environments, matter reveals its intrinsic nature, stripped of the kinetic disguises created by thermal motion. Quantum effects emerge into the macroscopic world, creating exotic states like superfluidity and Bose-Einstein condensation. Molecules form and persist that would be quickly destroyed in warmer surroundings. Structures endure that would melt or sublimate at higher temperatures. The cold places we have visited are not dead or static, as our warm, biased perception might initially suggest. Rather, they possess their own forms of dynamism, operating on different timescales and through different mechanisms than the heat-driven processes of our everyday experience. Nitrogen geysers erupt on frigid Triton, despite surface temperatures of negative 235 degrees Celsius. Ice flows like glaciers on Pluto, with movements imperceptible to human observation, but significant over geological time. Molecules form on dust grains in molecular clouds through quantum tunneling, a process that cold enhances rather than inhibits. Even the ultimate cold of the cosmic future, the heat death toward which the universe progresses, contains the seeds of potential activity through quantum fluctuations and the possibility of new phase transitions in the vacuum itself. The cold universe is not a finished story, but an evolving one, albeit operating at a pace and through mechanisms that challenge our warm world intuitions. Our journey has taken us across vast scales of temperature, from the few nanokelvin achieved in the coldest laboratories to the cosmic microwave background at 2.7 Kelvin, from the frozen methane lakes of Titan at negative 180 degrees Celsius to the frigid interiors of molecular clouds at 10 Kelvin. This spectrum of cold reveals the richness of low-temperature physics and chemistry, where each threshold crossed unlocks new phenomena and creates new possibilities for matter's arrangement and behavior. The progressive development of cold, from the merely chilly to the quantum extremes near absolute zero, mirrors in some ways the development of complexity in the universe. Just as cosmic evolution has proceeded from simple hydrogen and helium atoms to the intricate structures of galaxies, stars, and ultimately life, our exploration of cold has revealed increasing layers of subtlety and organization as temperatures drop. This parallel reminds us that both heat and cold play essential roles in creating the conditions for complexity, each necessary in its own domain. Perhaps nowhere is this more evident than in the role cold plays in star formation. The molecular clouds where stars are born must be cold enough for gravity to overcome the dispersive effects of thermal motion, allowing matter to collapse into protostars. Yet the result of this collapse is heat, the warming of gas until nuclear fusion ignites and a star begins to shine. Cold thus serves as the necessary precondition for the creation of cosmic heat sources, a paradox that highlights the complementary nature of these seemingly opposed states. This same complementarity appears in the cycles of Earth's climate and geology. The cold of winter is not the antithesis of the growth of spring, but its necessary precursor, part of the annual rhythm that allows life to flourish in its diverse forms. The ice ages that have periodically gripped our planet have not simply halted evolution, but have driven it in new directions, creating selection pressures that spurred adaptation and diversification. Cold, even when challenging to individual organisms, often fosters resilience and innovation at the level of ecosystems and species. The relationship between cold and life deserves particular reflection. We often associate cold with hostility to life, and indeed, most living organisms on Earth require temperatures within a relatively narrow range, centered well above the freezing point of water. Yet cold also preserves and protects. It slows the chemical reactions that would otherwise break down complex molecules. It creates stable environments where delicate structures can persist. In the proper context, cold does not oppose life but enables it, creating conditions where complexity can emerge and endure. Consider the remarkable adaptations of organisms in Earth's coldest environments. Arctic and Antarctic fish produce antifreeze proteins that prevent ice crystals from forming in their tissues. Certain frogs and turtles can survive being completely frozen, their metabolic processes suspended until warming returns. Tardigrades, the microscopic water bears, can enter a state of cryptobiosis in extreme cold, essentially shutting down all detectable metabolism until conditions improve. These adaptations reveal life's extraordinary capacity to accommodate and even utilize cold, suggesting that our warm-centric view of biology may be unnecessarily limited. This insight has profound implications for astrobiology, the search for life beyond Earth. If life can adapt to extreme cold on our planet, might it also have evolved to thrive in the frigid environments of other worlds? The subsurface oceans of Europa and Enceladus, maintained in liquid state by tidal heating despite surface temperatures of -160°C or colder, could harbor ecosystems entirely unlike those familiar to us. Even Titan, with its lakes of liquid methane and ethane at -180°C, might host chemical systems with life-like attributes, utilizing different solvents and biochemistry than Earth life, but achieving similar functions of metabolism, replication, and adaptation. This possibility expands our conception of habitability far beyond the traditional notion of a circumstellar habitable zone where water remains liquid on a planet's surface. Cold worlds with internal heat sources, whether from radioactive decay, tidal flexing, or primordial heat, might maintain niches where life could develop and persist indefinitely. The cold surfaces of these worlds would then serve not as barriers to life, but as protective shields, preventing the escape of volatile compounds and sheltering any subsurface ecosystems from cosmic radiation and meteorite impacts. The protective aspect of cold extends beyond biology to the cosmos itself. The cold of molecular clouds preserves the complex chemistry that eventually feeds star and planet formation. The chill of comets maintains a record of the early solar system's composition that would be lost at higher temperatures. The frigid surfaces of outer moons and Kuiper Belt objects preserve geological features for billions of years, allowing us to read the history of the solar system in their terrain. Cold is not the enemy of information, but often its guardian, slowing the processes that would otherwise erase the universe's memory. This preservative quality of cold has been recognized and utilized by human civilizations throughout history. From the ice houses of ancient Persia to modern cryogenic storage of biological samples, we have harnessed cold's ability to pause the processes of decay and change. In this way, cold gives us a unique relationship with time, allowing us to extend the useful life of food, preserve genetic material for future generations, and even, in the speculative realm of cryonics, potentially pause the journey toward death itself in hopes of future revival. The association between cold and time extends to our metaphorical language as well. We speak of cooling emotions, of taking time to chill out or to give a heated situation a chance to cool down. These expressions recognize intuitively what our scientific exploration has confirmed, that cold often relates to a slowing of processes, a creation of space for reflection and reconsideration. The cooling of the universe over cosmic time similarly creates the conditions for structure and complexity to develop, a necessary counterbalance to the chaotic energy of higher temperatures. There is a profound stillness to extreme cold, a quieting of the frantic motion that characterizes warmer environments. In this stillness, subtle signals emerge that would otherwise be lost in thermal noise. The most sensitive astronomical detectors operate at cryogenic temperatures, allowing them to detect the faintest light from the most distant galaxies. The human-created cold of quantum computers allows for the preservation of delicate quantum states that would quickly decohere at room temperature. In coldness, we find not an absence of information, but its clarification. This clarifying quality extends to the realm of human perception and aesthetics. The stark beauty of winter landscapes, where superfluous details disappear beneath blankets of snow and ice, reveals the essential forms and structures of the world. The simplicity and elegance of bare tree branches against a winter sky, the perfect crystalline symmetry of snowflakes, the muffled acoustics of a snowy forest, all create an environment that encourages contemplation and appreciation of pattern and form. Cold strips away the excess and reveals the underlying architecture, both in nature and in our perception of it. Throughout human culture, cold has played this clarifying role in our understanding of ourselves and our place in the cosmos. The Norse conception of Niflheim, the realm of primordial ice that balanced the fire realm of Muspelheim, recognized cold as a fundamental creative force rather than merely a hostile environment. The Buddhist practice of Tummo, or inner fire meditation, uses awareness of cold as a pathway to heightened consciousness and spiritual insight. The Japanese aesthetic of yukimi, or snow viewing, celebrates the transcendent beauty revealed when the familiar world is transformed by cold. These cultural expressions recognize what our scientific journey has confirmed, that cold is not merely privation or absence, but a distinct state with its own qualities and significance. Just as darkness is not simply the absence of light, but a condition that reveals the stars, so cold is not merely the absence of heat, but a state that reveals aspects of reality obscured in warmer environments. The coldest places in the universe show us matter and energy in their most fundamental forms, stripped of the complications added by thermal agitation. This stillness also invites contemplation. There is a reason why the silence of a snowy landscape evokes feelings of peace and reflection. Cold environments, with their reduced sensory stimulation and slowed processes, naturally incline the mind toward deeper thought. The cold places of the cosmos, while far beyond human experience, evoke a similar response when we contemplate them, a drawing inward of awareness and an opening to larger questions about existence and meaning. The quieting effect of cold appears even in our response to the knowledge of the universe's thermal future. While the heat death might initially seem a bleak prospect, many find a certain peace in the vision of a universe gradually settling into perfect equilibrium. There is completion in this image, a sense of rest after the long creative work of cosmic evolution. The cold future offers not annihilation, but resolution, a natural conclusion to the thermodynamic story that began with the intensity of the Big Bang. This perspective reveals another quality of cold, its relationship to patience and endurance. Cold processes often unfold over vast timescales, from the slow evolution of ice sheet topography over millennia to the gradual cooling of stellar remnants over billions of years. The cold universe operates without haste, allowing structures to develop and patterns to emerge through the gentle but persistent action of physical laws. This patience stands in contrast to the rapid, often destructive processes associated with extreme heat, offering a different but equally necessary aspect of cosmic creativity. Our human relationship with cold reflects this duality of challenge and opportunity. We have developed elaborate technologies to shelter ourselves from cold, from the simplest animal hide clothing of our ancestors to modern heating systems and insulated buildings. Yet we have also learned to use cold constructively, harnessing its preservative qualities for food storage, its thermal gradients for generating electricity, and its extreme forms for scientific research. Like all relationships with fundamental aspects of our environment, our engagement with cold involves both respect for its power and creativity in using its unique properties. Perhaps one of the most remarkable aspects of cold is how it connects the cosmic and the quantum scales. The coldest natural environments in space and the coldest artificial environments in laboratories both reveal quantum phenomena that remain hidden at higher temperatures. The superfluid behavior of liquid helium at temperatures below 2.17 Kelvin mirrors, in some ways, the coherent quantum state of a Bose-Einstein condensate at a few nanokelvin, both representing matter's transition from classical to quantum behavior as thermal motion subsides. This connection reminds us that the same fundamental laws govern phenomena across all scales, from the subatomic to the cosmic. The beauty of cosmic cold places manifests in forms both familiar and alien. The delicate crystal structures of snowflakes have their cosmic counterparts in the nitrogen ice patterns of Triton and the methane snow-capped mountains of Pluto. The rippling curtains of Earth's auroras find parallels in the dynamic atmospheres of the ice giants, where cold chemistry creates some of the most vibrant colors in the solar system. Even the perfect black-body spectrum of the cosmic microwave background, the afterglow of creation itself, possesses a mathematical elegance that translates into a kind of austere beauty. This beauty often emerges from the interplay of simplicity and complexity. At very low temperatures, physical systems tend toward their ground states, the simplest configurations available to them. Yet from these simple foundations, complex patterns can emerge through processes of self-organization and the influence of subtle forces normally overwhelmed by thermal effects. The result is a kind of emergent complexity, where intricate structures and behaviors arise, not despite the simplicity of cold systems, but because of it. This principle operates across scales, from the formation of snowflakes to the filamentary structure of galaxy superclusters. Our exploration of the coldest places in the universe has also revealed the limitations of our ordinary language and intuition. We speak of cold as if it were a thing in itself, but our scientific understanding reveals it as a relative state, a measure of thermal energy's absence rather than the presence of some cold substance. The ancients who imagined cold as a kind of fluid or essence were not entirely wrong in their intuition that cold has positive qualities, but modern physics gives us a more precise understanding of these qualities as emerging from the behavior of matter and energy at low thermal excitement. This refinement of understanding exemplifies the broader process of science, which often begins with intuitive categories from everyday experience, but progressively replaces them with more precise concepts that may initially seem counterintuitive. Our journey through cosmic cold has taken us far beyond the simple hot versus cold dichotomy of daily life into a rich landscape of quantum states, phase transitions, and emergent properties that depend sensitively on exact temperature conditions. This progression reminds us that scientific understanding, while building on common experience, often leads to conceptions of reality far richer and stranger than our starting intuitions. The human-created extreme cold of laboratories near absolute zero represents a particularly striking example of this progression. By developing technologies to achieve temperatures far colder than any natural environment on Earth, scientists have opened windows into quantum realms previously accessible only through mathematical theory. The visualization of quantum wave functions in Bose-Einstein condensates, the direct observation of quantized vortices in superfluids, the manipulation of individual atoms in optical lattices. All these achievements represent not just technical triumphs, but transformative expansions of human perception into realms fundamentally different from our everyday experience. These achievements also highlight the extraordinary adaptability of human cognition and technology. Though we evolved as warm-blooded creatures on a relatively warm planet, we have developed the capacity to imagine, create, and in some ways inhabit through our instruments environments utterly alien to our biological nature. Our ability to comprehend the physics of systems at a few nanokelvin, or to model the behavior of matter in the cold voids between galaxies, demonstrates the remarkable flexibility of intelligence, its capacity to transcend the conditions of its own emergence. This adaptability suggests intriguing possibilities for the future relationship between intelligence and cold. As the universe continues its inexorable cooling, any long-lived civilization would need to accommodate itself to ever-decreasing energy availability. Some theorists have suggested that the most efficient computational processes might actually operate better at very low temperatures, where thermal noise is minimized and quantum coherence can be maintained. Perhaps advanced intelligence in the distant cosmic future might not struggle against the encroaching cold, but embrace it, developing substrates and processes optimized for low-temperature operation. Such speculation necessarily remains tentative, but it highlights a broader theme of our journey: the way cold environments often require and reward different strategies than warm ones. In biology, cold-adapted organisms typically emphasize efficiency and conservation rather than rapid growth and reproduction. In human cultures, societies in cold regions often develop strong emphases on planning, storage, and community cooperation to survive long winters. If similar principles apply at the civilizational or post-biological level, the cold future of the cosmos might favor forms of intelligence that emphasize efficiency, conservation, and extremely long-term planning over rapid processes and expansion. This perspective offers a counterpoint to the sometimes bleak presentation of the universe's thermal future. Rather than seeing the progression toward cold as simply the end of all interesting processes, we might recognize it as a transition to different modes of organization and activity, operating on timescales and through mechanisms unlike those familiar to us but perhaps no less rich in their way. Just as the cold environments of today's universe host phenomena impossible in warmer regions, the cold future might permit forms of organization unavailable in the current, relatively energetic cosmos. As we contemplate these possibilities, we might also reflect on how our journey through cosmic cold places has altered our perspective on our own world and lives. The knowledge that we inhabit a warm island in an increasingly cold cosmos can inspire both gratitude for our favorable circumstances and awareness of their transience on the grand scale. The heat that makes Earth habitable, ultimately derived from the Sun's nuclear furnace and our planet's radioactive interior, represents a temporary condition in cosmic evolution, a brilliant but brief interval in the universe's long progression from the heat of the Big Bang to the cold of heat death. This awareness need not be cause for despair, but might instead foster appreciation for the remarkable moment we inhabit. We exist at a time when stars still shine, when energy gradients still drive complex processes, when matter remains organized into structures as intricate as galaxies, planets, and living organisms. The cold places we have explored provide contrast that highlights the special nature of our warm world, not as the norm, but as a precious exception, a brief flourishing of heat-driven complexity in a cosmos trending toward cold simplicity. There is wisdom in this perspective, an invitation to value the warmth of our sun, our planet, our bodies, and our communities, not as permanent entitlements, but as extraordinary gifts to be cherished during their time. The cold places of the universe remind us that energy and motion, the foundations of all we experience, exist in limited supply, gradually dispersing across an expanding cosmos. Against this background, the concentrated energy that enables consciousness itself appears all the more remarkable. A fleeting arrangement of matter and energy, capable of comprehending its own nature and the broader cosmic context from which it emerged. In this light, the coldest places in the universe offer not a nightmare vision of hostile emptiness, but a reminder of the preciousness of warmth and the miracle of complexity arising from fundamental physical processes. They invite us to appreciate the remarkable universe we inhabit, with its full spectrum from the heated cores of stars to the frigid expanses between galaxies, each temperature regime playing its role in the grand cosmic narrative. The cold regions, rather than standing in opposition to life and consciousness, form part of the necessary context that makes islands of warmth and complexity possible. As our journey concludes, perhaps what remains most valuable is this perspective it offers. We exist in a universe trending inexorably toward cold, yet we find ourselves precisely in that remarkable middle period when temperatures allow for the complexity of stars, planets, and life. Our warm existence is not the default state of the cosmos, but a temporary, precious interval between the extreme heat of the Big Bang and the extreme cold of the heat death. This knowledge might foster both humility about our place in cosmic history and appreciation for the extraordinary conditions that allow us to exist and contemplate our existence. The cold, in the end, is not our enemy, but our context, the background against which all warmth and life stand out in brilliant contrast. Like the darkness that allows us to see the stars, the cold of the cosmos provides the setting in which the light and heat of creation can shine most vividly. Without the vast cold spaces between stars, the stellar furnaces themselves would have no meaning, no purpose in the cosmic narrative. It is the interplay between heat and cold, between energy concentration and energy dispersion, that creates the dynamic universe we observe and inhabit. As you drift towards sleep, consider yourself a remarkable warm anomaly in a predominantly cold universe, a temporary arrangement of atoms capable of wondering at the stars. The very materials of your body were forged in stellar furnaces before being scattered into space, cooling as they traveled, eventually condensing into planets where the delicate balance of heat and cold made life possible. You are, in a very real sense, the universe experiencing itself, matter and energy arranged into a brief but wondrous pattern of consciousness. The coldest places in the universe are not empty, they are patient, they are quiet. And in their silence, the story of everything continues to unfold. Sleep now, beneath the stars, wrapped in the stillness of the cosmos.